Historically, the biggest empires always had the biggest navies or the biggest armies, the most ships, the most men, or both. And in the modern age, science and industry have repeatedly pushed the limits of men, technology, and imagination in the pursuit of that power. More often, not by creating bigger armies, but bigger weapons. From aircraft that defy gravity, tanks to field guns, bombers to battleships. The destructive capability of the machinery of war develops with each decade, each unique in their own way. The machines in this episode share two common traits. They are big and they are powerful. In World War I, guns began to assume monumental proportions. Big Bertha, the German siegebreaker, could hurl an 800-kilogram projectile 13 kilometers and was used to devastating effect in the early stages of World War I. But during World War II, a class of even larger supercannons emerged, and their psychological effect on the men facing them meant that, like Bertha, they all had personalized names. And one of the biggest was called Annie. Annie was one of 25 massive railway guns designed and built by the famous German Krupp Steelworks prior to the commencement of World War II. Designated the K5, they were developed to deliver shells capable of destroying the French border fortifications known as the Maginot Line.
The first objective was to deliver a large projectile containing a large amount of explosive to the target. The second objective was to provide range, and some of the quarter-of-a-ton projectiles were able to reach 50 kilometers.
Although they never saw service on the Maginot Line, they were involved in a variety of sieges. And for Annie, that most famously took place during the American invasion of the Italian coastal town of Anzio in early 1944. Annie was one of two K5s moved and hidden in rail tunnels, 18 miles above the coastline where the Americans had landed. From this vantage point, over 2 months, the pair rained down their massive exploding shells on the 70,000 Allied troops trying to break out of the established beachhead. It was during this time that the train-like sound the huge shells made as they passed overhead earned the guns the nicknames Anzio Annie and the Anzio Express. And the K5's 288mm caliber barrel was rifled with 12 7mm grooves, making it not just big, but extremely accurate. Each K5 railway battery consisted of 2 guns. Each gun had its own train, with engine and 6 rail cars. Ultimately, it was that size that proved her downfall.
For a railway gun, you had to lay tracks to get it to its destination. Now, not only was that intensive in terms of manpower, but also, inadvertently, what you did was, when you were laying these tracks, you were providing a path for the Allied bombers to track where that railway gun actually was. So its survivability was put into question by virtue of the fact of the tracks that it was running on.
The railway gun's great advantage of being able to use existing infrastructure to besiege armies was, paradoxically, its Achilles heel. when on January 20th, 1953, at the height of the Cold War, former World War II General Dwight D. Eisenhower became President of the United States. His inauguration parade included 65 bands, floats from the then 50 states of the Union, 22,000 servicemen and women, 350 horses, and a gun. A brand new 280mm cannon.
In the early 50s, they were exploring how to deliver nuclear payloads. And there was a series of tests in Nevada where they tested a variety of different delivery systems.
One of which was the M65 howitzer. With missiles capable of delivering atomic warheads, the most powerful weapons on the planet, in the control of the U.S. Air Force, the U.S. Army felt it too should have a weapon of similar force. And when in 1949, the U.S. Atomic Energy Commission announced the development of a 280mm caliber nuclear projectile, the Army set to work developing a mechanism to deliver it. The result was a self-propelled gun with an overall weight of 78 tons, a length of 26 meters, and a width of 5 meters. Advances in mechanics meant that, once in position, Atomic Annie could be set up in 15 minutes. And in May 1953, in the deserts of Nevada, the weapon was tested.
And they did actually fire an 800-pound nuclear shell from a 280mm artillery piece 7 miles in the Nevada desert to explode as a nuclear device. It's the only time, certainly in the Western world, that a nuclear shell had been delivered by a cannon.
Nine M65s were deployed in Europe to counter the Soviet threat. But Atomic Annie, like Anzio Annie, was a transportation nightmare. On the road, it resembled a large fire engine, with 2 prime movers using independent steering systems, one positioned at either end of the gun carriage. Its propensity to tip over earned it another less favorable nickname, the Widowmaker. Evolution sometimes heads in a direction that doesn't quite work, and nuclear technology did not find a natural place fired from a gun. As the end of 1962 approached, the idea of the stately and visible progress of an atomic cannon moving across the world as a crucial influence had passed. New weapons had been developed, and the Atomic Annies joined their cousins, the K5s, in retirement.
All were withdrawn from service, along with their 80-odd shells constructed for them.
What history has shown us is that power is not always about sheer size. The punch of a behemoth doesn't necessarily have to come from a behemoth. And in the case of the M777, while it is still a large weapon, 155mm in caliber, and with an overall length of 10 meters, the focus of its development was on reducing its weight, which makes it extremely powerful.
And that means that the M777 could be transported in a larger range of helicopters than its previous counterpart. And so, in that regard, it can be a much more deadly weapon because the military can get it to where it needs to be quickly.
The M777 tips the scales at just over 4 tons. To achieve this low weight, it applies the latest advances in metallurgical science, and its construction makes extensive use of a rare metal that has found numerous applications in the modern machinery of war: titanium.
Now, titanium has a density which is about half that of steel, but it's a very strong material. So it means that you can reduce the weight of your structure, but at the same time maintain strength that you need when you're dealing with the high shock forces when the gun fires projectiles.
Everything about the M777 is a stark example of more for less. It's operated by a crew of 5. Anzio Annie had a crew of 82. The M777 can rapid fire 5 rounds per minute. Annie fired one every 5 minutes. And while Annie was accurate, modern shells like the Excalibur take accuracy to a new level.
So the Excalibur is a shell which has a little sort of motor that kind of deploys fins on firing and can actually use these fins to intelligently guide the shell to its target.
A lightweight behemoth with incredible power and accuracy. One of the few things the M777 can't do is move itself. And a barrage is of little use if you can't press your advantage. To do that, you need to get up close. Necessity, they say, is the mother of invention. The mass of wire, mud, trenches, and modern weaponry on the Western Front during World War I had led to an appallingly costly stalemate, where success was measured not in kilometers gained, but mere meters. But on the 8th of August 1918, at the Battle of Amiens, on a single day, the Allied forces moved 13 kilometers across German-held territory. And on that day, the battlefield hummed with the sound of over 550 of what would prove to be perhaps the defining weapon of the war. Tanks.
When the British were designing the tank in 1915, 1916, they were aware of the nature of trench warfare on the Western Front. And the reason for this large track design in that lozenge shape of the first tanks was to give the tank mobility. So if it came to the trench lines, if they were able to break through, is that they'll be able to cross them without falling into a trench and getting irrevocably bogged.
The 28-ton rhomboid-shaped Mark I tank first saw service on the Somme on the 15th of September 1916 and was not a huge success. Mechanical problems from what proved to be an underpowered and unreliable 78-kilowatt engine and crews inexperienced in handling the new weapon compromised the performance of the few that made it to the battlefield. And they were slow.
It actually was slower than an infantryman walking, which meant that rather than being the tanks advancing and the troops coming behind the tanks, it often meant that the troops went far in advance of the tank, which found it hard to keep up.
Noise inside the tank made it difficult to communicate, and as a result, some became hopelessly lost. Others ground to a halt, their crews rendered unconscious by the fumes of the engine, which sat in the middle of the fighting compartment without any cover or muffler. And they were prone to bogging in the muddy morass that was the Western Front. But development persisted. Adjustments to each variation were made based on combat experience. In the Mark IV, power was up to 15 kilowatts. Weight was down to 25 tons. Speed increased to 6.5 kilometers an hour. Continuous improvements that by 1918 saw the tank entrenched as a vital cog in the machinery of war.
You think of the emergence of the tank on the battlefield in the First World War. It's clunky, it's unreliable, the armour's perhaps penetrated by rifle or machine gun fire, but nonetheless it's this lumbering, terrifying beast of war you've never seen before. It has an immense psychological impact. And it becomes tactically very significant. As a soft, squishy infantryman with a rifle, you are absolutely outclassed. by this giant land ship. And that remains true for decades.
And within just 2 of those decades, tank warfare reached its zenith with the outbreak of World War II and the famous German Blitzkrieg tactics of 1939. A highly mobile and destructive all-arms method of fighting, led by the famous Panzer tanks. Blitzkrieg reshaped the battlefield, where previously emphasis had been on a smattering of light tanks and infantry support roles. The Allies now desperately needed medium tanks that could compete with and defeat the German panzers. But in tank design, the British had fallen well behind the game.
The British in 1918, it can fairly be said, were probably the leaders in tank design. However, the belief that tanks would be useful in European war, but probably not in the colonial warfare which the British find themselves doing in the interwar period, meant that they did not spend as much time looking at tank design as they did until probably late in the 1930s.
Outclassed and with limited time and limited resources, they turned to the Americans for salvation. They responded with the M4 Sherman, the most widely used tank by the Western Allies during the war. The design brief was simple: a medium tank with a 75mm main gun mounted in a full traverse turret. Fast enough to keep pace with the German tanks, with good all-round visibility and improved armor allocation. And it was needed almost immediately. To save time, the Americans incorporated the engine, transmission, tracks, and suspension systems of the M3 Lee medium tank. On that existing chassis, they put an all-new body with frontal armor that was not a patchwork of riveted plates, but a solid piece of cast homogeneous steel 50mm thick. To overcome the strength disadvantage of cast armor, the front armor plate was cleverly sloped to 56 degrees, creating a surface that would cause some incoming rounds to glance off. But more importantly, it increased the effective thickness of the armor on the horizontal plane to 91mm, almost doubling protection. Even so, against the heaviest of tanks, the Sherman was vulnerable.
Crews putting extra track on the front of their vehicles, they're putting extra sandbags on the front of the vehicles, and this is trying to retard an incoming armour-piercing round. Sometimes not to great effect.
Weighing close to 30 tons, the Sherman had a top speed of 40 kilometers per hour, meaning it could keep pace with its principal foe, the Panzer. And armed with a medium-velocity 75mm main gun, 2 anti-infantry machine guns, and a 50 caliber Browning anti-aircraft gun, they had the Panzer covered. But the Sherman's greatest strengths were its reliability and its numbers. Nearly 5,000 were produced, built by the giants of the American motor industry: Ford, Chrysler, and General Motors.
That whole Henry Ford type thing, the production line of cars, now applies to making a tank.
The Sherman's life was extended, seeing combat in numerous Cold War conflicts. But as anti-tank weaponry improved and the speed of warfare increased, the need arose for battlefield behemoths that were simply bigger and faster. And there are none bigger than the tank they call Whispering Death. The Cold War fueled an environment which led to the development of some of the most advanced weapon systems on the planet. And when in the 1970s, the US Army decided they needed a faster tank with exceptional firepower and unprecedented levels of crew protection, they took the best of the world's available military technology and created the M1 Abrams. Learning lessons from a variety of conflicts, they designed a tank that, despite weighing up to 70 tons in some variants, has a deceptively low profile. Standing less than 3 meters tall, the low height makes the Abrams a less obvious and less available target for enemy fire. Significant work has also been done to reduce the thermal signature of the tank, making it harder to detect. But if it is hit, it is constructed using the most advanced armor available.
The protection system of the M1 Abrams is fairly superior compared to a lot of main battle tanks. And certain variants of the M1 Abrams actually use depleted uranium in the turret. Now, depleted uranium is a very dense material, and that means it's able to provide superior levels of protection against a whole range of weapon systems.
It was also the first tank to use the British-developed Chobham armor, a complex laminate structure that combines an arrangement of ceramic blocks, metal plates, Kevlar, and open space to achieve a near-perfect blend of anti-penetration surfaces. In battle, the Abrams 120mm smoothbore main gun has been found to outrange any other tank in current service. And connected to the world's most advanced tank-based targeting system that monitors the tank's tilt, motion, and even the wind, it allows the Abrams to fire on multiple targets with accuracy while on the move. But what truly sets the Abrams apart is its speed, which can exceed 70 kilometers per hour. To achieve this, it uses a distinctive power source.
The use of the gas turbine engine in the M1 Abrams is fairly unique to main battle tanks. And the reason why they use a gas turbine is simply to reduce the noise and to give it the power it needs to accelerate such a heavy vehicle. This vehicle weighs up to 70 tons with certain variants, and so it's a very heavy piece of military equipment, and you need a substantial means of driving that forward.
It is the whisper-quiet gas turbine that has given the M1 its nickname. A power source that is normally associated with a very different kind of battlefield behemoth: aircraft. On the 6th of August, 1945, an event took place that would change the world forever. The heaviest bomber of World War II delivered a device that would create the biggest explosion mankind had ever experienced. Less than 30 years previously, heavier-than aircraft had been little more than curiosities. But the aircraft that carried that fateful payload in August 1945 was a far cry from the timber and fabric of World War I. It was a heavy bomber that revolutionized military and civilian aviation. Militaries always want aircraft with increased speed and payload, but in World War II, what the Americans desperately needed was one with greater range to deal with the huge distances covered in the war in the Pacific. To achieve a lethal combination of speed, payload, and range, they based their designs on an aircraft that was already the supreme bomber of World War II, the B-17 Flying Fortress, and built the largest, most complex aircraft that had ever gone into production.
The Flying Fortress was a very capable aeroplane, but it was firmly rooted in the 30s, and it had been developed as far as it could realistically go. With the B-29, they designed it to do everything a Flying Fortress could do and do it all better.
The B-29 was a combination of cutting-edge technology and devastating firepower, wrapped in a massive package. Fitted with 4 of the largest radial engines manufactured in the United States, the supercharged 18-cylinder Wright R-3350 The Superfortress had a top speed of over 550 kilometers per hour and a combat range of 5,220 kilometers, double that of the B-17. And it was designed for sustained flight at what was then dangerously high altitude. As you ascend, temperature drops 1 degree per 300 meters. Without heating and oxygen, anoxia can result in death within 10 minutes at altitudes over 7,500 meters. To overcome this, the B-29 became the first production aircraft to feature a fully sealed and pressurized cabin.
It allowed them to fly routinely over 35,000 feet, where the air is thinner and therefore you can fly faster without putting as much strain on the engines to maintain the speed.
The B-29 was in every way a technological marvel. A systems-driven aircraft with over 10 kilometers of electrical cabling, part of which fed a state-of-the-art analog firing system that remotely trained the aircraft's 5 gun turrets on incoming targets, compensating for speed, gravity, and atmospheric pressure. Intercontinental range, payload, and versatility made the B-29 a game-changer that not only helped end the war, but paved the way for both the Americans and the Soviets to pursue even grander designs. Designs that would allow them to deploy greater payloads to war zones with unparalleled speed. It started a game of brinkmanship, a race to be the biggest. A race the Soviets would ultimately win. During the latter stages of the Cold War, when the Americans unveiled the massive C-5 Galaxy transport, the Soviets immediately countered and produced an aircraft that remains the largest airborne military transport vehicle in the world today. Known by NATO as the Condor, it is the Antonov AN-124. Big machines need a big aircraft to lift them. Designed to carry the largest Soviet tanks, troops, and support equipment and deliver them to a hotspot quickly, the AN-124 has a maximum takeoff weight of 405 tons with a payload of 150 tons. To put those weights into perspective, it can carry 2 fully loaded B-29s, throw in a fully loaded B-17 for good measure, and still have room to spare.
The design of large transport aircraft require the right combination of the design of a fuselage that can accommodate the potential payloads that may be required during its operation. Included in that is the access to the payload.
With a fuselage close to 70 meters in length and 21 meters in height, creating a cargo space 36 meters long and 6.4 meters wide, comparable in size to a bowling green, the sheer size of the aircraft presents a unique design challenge.
Larger fuselage will affect the aerodynamics of the aircraft, it will increase the drag of the aircraft, and so you have to balance that with wings that are large enough to generate enough lift, and also, quite principally, the engines that develop enough thrust to lift these aircraft.
To generate that required lift, the AN-124 has a wingspan of 73 meters, and with an upper deck that can accommodate 88 fully equipped soldiers, it can deploy a small army at over 1,000 kilometers per hour. The AN-124 is big and fast, but on its own, not lethal. The Tupolev Tu-160, on the other hand, is all three. Known by the NATO codename Black Jack, or the White Swan in Russia, the Tu-160 was the last bomber aircraft produced by the Soviet Union before its collapse, and is the largest jet-powered swing-wing combat aircraft ever to enter service. An aircraft again born of the military tit-for-tat that was the Cold War. when the Americans began developing a similar aircraft, the B-1.
The Americans were developing a supersonic swing-wing bomber that could quickly penetrate Soviet airspace. During that development, interestingly, the Americans actually decided perhaps that need wasn't there, and so the Americans actually cancelled the B-1A program. The Russians, however, continued with the Blackjack and developed that aircraft into a very capable, very high-speed, penetrating bomber.
All supersonic aircraft have swept wings. Put simply, the faster you go, the less wing area you need to generate lift. But at low speeds, that lift is greatly reduced. The engineering challenge was to produce an aircraft with enough lift to raise a serious payload, but one which could also reach speeds comparable to a modern fighter jet.
And one solution for that is so-called swing wings. During low-speed operation at takeoff and when you return for landing, the wings are swept forward so that they are what we call very high aspect ratio wings. And that configuration of wing is optimized to generate lift very efficiently, especially at low speeds.
The variable geometry outer tapered wings of the White Swan are able to be swept back from 20 degrees to 65 degrees, providing high-performance flight characteristics at both supersonic and subsonic speeds. And the tail surfaces, horizontal and vertical, are one piece and all moving for improved low-speed control. Equipped with 4 of the most powerful engines ever fitted to an aircraft, the Tu-160, which weighs 275 tons fully loaded, manages an extraordinary top speed of 2,200 kilometers per hour and climbs at a rate of 70 meters per second to a service ceiling of 16,000 meters. But while a behemoth in the air or on the land can be measured in terms of bowling greens, at sea, the word behemoth takes on a whole other meaning. For centuries, a nation's naval strength determined its place in the world. And as the centuries passed, ships slowly increased in size. But the Industrial Revolution sped that growth. Engines created a new source of power. Power gave rise to bigger ships with heavier guns, and heavier guns led to heavier armor. And in the early 1900s, a naval arms race led to the creation of ocean-going behemoths of such size that they defied imagination. Battleships.
The battleship really, I suppose you could say, reached its zenith during World War I. It was a large steel ship, heavily armoured, fitted with big guns which could sling tons of shells towards an enemy battleship. Since then, battleships continued to be used through the Second World War, but more as large gun platforms than the traditional engagement between 2 battle fleets steaming in parallel, endeavouring to sink each other.
And in the Second World War, one of the biggest of those gun platforms was the American Iowa class. World War II saw a shift in the shape of naval warfare. The Americans' new and fast Essex-class aircraft carriers had stolen the battleship's mantle as the capital ships of the fleet. But they needed vessels that could protect them at speeds in excess of 30 knots. The design challenge was to develop a battleship fast enough to keep pace, while also providing the firepower to combat the heavy Japanese vessels already constructed. At over 270 meters in length, and with a beam of 33 meters, everything about the Iowa class was big. 8 water tube boilers, feeding 4 advanced steam turbines, gave the Iowa a top speed of over 33 knots. And to guard against torpedoes, the Iowa class had a hull design that included an internal bulge, consisting of 4 longitudinal bulkheads behind the outer hull plating, with a depth of 5.5 meters, designed to absorb the energy of a torpedo warhead, protecting the superstructure. But a battleship is nothing without big guns, and the Iowa class carried 9 massive Mark 7 main guns, each with a caliber of 410 millimeters. Perhaps the most well-known of the Iowa class was the USS Missouri, with the Japanese famously signing the surrender ending World War II on her deck on the 2nd of September 1945. Decommissioned a number of times before being brought back into service, first in Korea in the 1950s and again in the 60s, where her massive guns provided extra firepower in Vietnam. The Missouri was finally decommissioned in 1992 after being resurrected yet again during the First Gulf War. But not all battleships were survivors. Hitler, at one time, referred to the First World War German fleet as a romantic plaything, a parade piece. If Germany were to fight again, under Hitler, they would have a navy to be reckoned with. And by 1939, Germany boasted a modern fleet of staggering proportions. And the centerpiece of that fleet were 2 50,000-ton battleships, the Bismarck and the Tirpitz. The largest battleship class in Europe, these 250-meter-long behemoths had a top speed of 30 knots and a range in excess of 16,430 kilometers. In the Battle of Denmark Strait on the 24th of May, 1941, the Bismarck and the Prins Eugen engaged the British battleships, the Prince of Wales and the Hood. After only 8 minutes of firing, the Hood took a hit in her rear ammunition magazine, and 100 tons of cordite exploded, breaking the ship's back. She quickly sunk, taking all but 3 of her crew of 1,419 men with her. The Prince of Wales was also damaged and laid a smokescreen to cover her withdrawal. In those 8 minutes, Bismarck had fired 93 armor-piercing shells and had been hit by 3 shells in return. 1 had struck the forecastle, and 2,000 tons of water flooded the ship, contaminating fuel oil stored in the bow. Forced to change course to seek repairs, the Bismarck was pursued by the Royal Navy. Over the ensuing 2 days, the German vessel took a surprising number of hits and still managed to evade her pursuers. And it was armor that was the key to the Bismarck's survival. Nearly half of the vessel's overall weight constituted protection to vital areas. At the belt line, it reached 320 millimeters thick. On the decks, 120 millimeters. And the main gun turrets were shrouded by steel 360 millimeters thick. What did it for her in the end were the machines that spelled the end of the battleship as a machine of war: aircraft. On the 26th of May, a flight of 15 Swordfish torpedo bombers launched an attack. Within just hours, the pride of the German fleet was sunk.
What's really fascinating about the action against the Bismarck was that the aircraft, the Swordfish, the most basic, simple little aircraft with torpedoes slung underneath it, operating from an aircraft carrier. I mean, the aircraft were technologically ancient.
The ship that launched those aircraft was one of a new type of warship that would hold sway for decades as one of the most powerful of all the machinery of war, and one of the biggest. The aircraft carrier. The British began using ships to carry aircraft in World War I. The first was the HMS Ark Royal, a heavily modified merchant ship that transported float planes in her hold, which were slung over the side using cranes. Despite not being a carrier as we know them, she introduced a number of features which are typical of aircraft carriers today.
An enclosed hangar, which contains the aircraft, a clear deck forward so that you could launch aircraft from there, and workshops to provide all the means of supporting those aircraft. The ship unfortunately only had a speed of about 10 knots, so she was not very capable of high-speed operations or real use as an aircraft carrier.
Those real, purpose-built aircraft carriers emerged in the 1930s. And in the early days of 1941, among the ships which gave chase to the Bismarck was one of them, also named Ark Royal, and launched in 1938. Far from being a converted merchant ship, HMS Ark Royal displayed the two most distinctive features of a modern aircraft carrier. A flat 240-meter flight deck that overhung the stern 20 meters above the waterline, and the familiar control tower island positioned on the starboard side. With armored hangars extending 3 stories below, the 50 aircraft that made up her strike weapons were raised to the deck by hydraulic lifts. Equipped with the now famous arrestor cables to catch the aircraft on landing, the Ark Royal used the latest steam catapult system to assist them at takeoff. With those aircraft comprising the Ark Royal's primary weapons, she was lightly armed. But with a top speed in excess of 30 knots, Britain's military planners believed they would be able to outrun most enemy ships if attacked. This thinking also led to the Ark Royal being relatively lightly armored. And it cost her. In November 1941, while sailing toward Gibraltar, the Ark Royal fell victim to the German U-boat U-81. Sunk by torpedoes, just as the Bismarck had been only months earlier. But where aircraft carriers really came into their own was in the vastness of the Pacific. And their experiences would change the face of warfare forever. One of the early lessons of the Second World War was that the rapid advances in aircraft performance and capabilities during the interwar years meant that command of the air became a prerequisite to success in land or sea engagements. The superior range, flexibility, and effectiveness of carrier-launched aircraft was no more ably demonstrated than on the morning of the 7th of December, 1941. When a Japanese task force that included 6 aircraft carriers attacked Pearl Harbor, and in a little over 2 hours, decimated the American Pacific Fleet. The U.S. immediately responded by declaring war on Japan and began planning a reprisal. What the Americans wished to do was attack the Japanese where they least expected it, on their own soil. And to do that, they drew on a growing understanding of the aircraft carrier's potential.
You can approach your enemy territory and exercise your influence by means of force with your aircraft from your ship. You don't need a land base. You don't need somebody else's territory to operate from. You can operate from your own ship in international waters.
The reprisal attack became known as the Doolittle Raid, and it was carried out using one of the new Yorktown-class aircraft carriers, the USS Hornet. The Hornet had a wartime complement of close to 3,000 and was capable of carrying a mix of 90 aircraft, including torpedo bombers, fighters, and dive bombers, giving her an unmatched ability to respond to all manner of situations. And in April 1942, she steamed towards Japan carrying a special unit of 16 highly modified B-25 Mitchell medium bombers, under the command of Colonel James Doolittle. Although none of the B-25 pilots, including Doolittle, had ever taken off from a carrier, on the morning of the 18th of April, in a heavy gale, all 16 aircraft launched safely, and from a distance of over 1,000 kilometers, began their journey towards Japan. The aircraft began arriving over Japanese cities at about noon, 6 hours after takeoff, and attacked military and industrial targets in Tokyo, Yokohama, and Osaka. None were shot down, but landing medium bombers on the Hornet's 245-meter flight deck would be impossible for the aircraft, which were deliberately ditched over China following the raid. All of the aircraft were lost, but all bar 11 crewmen emerged unscathed. The Doolittle raid was the first American attack on the Japanese homeland, and not only bolstered morale at home, but in demonstrating the reach of American naval and air power, it had a deep psychological effect on the enemy. It also marked the emergence of the aircraft carrier as the dominant force in the war in the Pacific. As aircraft grew in size and power, they also grew in consumption. And the Cold War prompted a desire for warships that could operate without restriction.
Now, of course, in the aircraft carrier, if you can provide the propulsive power without needing all fuel, you've got an advantage. And the nuclear reactor provides that advantage. You don't need to fuel the aircraft carrier for our own propulsion. And you can use the space which is freed up to carry fuel for the aircraft.
The first American nuclear carrier was the Enterprise class, which saw service for 50 years. It was followed by the Nimitz. The Nimitz class is over 330 meters in length, displaces 100,000 tons, and can carry its cargo of 90 aircraft, which are launched from a flight deck with a total area of over 18,000 square meters that sits 20 stories above the surrounding sea. And it cruises at 32 knots, a speed it can maintain for 25 years.
A warship does all its work at sea, in any conditions. And a warship has to take the crew and the weapon systems to sea, keep the crew fed, fit, and working under any conditions, and to be able to fight under those conditions. This imposes considerable challenges on the way you design a warship and their survivability at sea.
Survivability was central to the Nimitz design, and being powered by two modern and relatively small Westinghouse nuclear reactors allows a lot of hull space to be dedicated to that survivability. As such, over 14 million liters of aviation fuel is stored on board. Added to that is the capacity to stow over 3,000 tons of ordnance. The Nimitz carries the latest in passive and active defense systems. However, the U.S. Navy still bears the scars of World War II. As a consequence, the aircraft hangars on board are divided into 3 fire bays on each level by thick steel doors that are designed to restrict the spread of fire. A feature present on all U.S. aircraft carriers since the devastating fires caused by kamikaze attacks over 70 years ago. The 10 Nimitz-class aircraft carriers, once the largest warships on the planet, are one of the most devastating of all the machinery of war. Now, however, their mantle as the largest falls to the Gerald R. Ford class. Designed like the Nimitz with a lifespan of 50 years, history suggests that her replacement will be even bigger. The ancient Chinese military strategist Sun Tzu wrote that all warfare is based on deception. And on the modern battlefield, deception means stealth. In the 21st century, being unseen to the enemy has become a dominant focus of military technology. From deadly snipers to aircraft that are invisible to the most sensitive tracking systems. From surface ships that seem to vanish, to the ever-increasing sophistication of the silent killers beneath the waves. The quest to be unseen continues to change the way we engage in battle. This is the story of stealth. The role that aircraft play in battle has changed dramatically since the First World War. No longer simply airborne observation platforms, today's aircraft are a vital part of a mobile attacking force. And to be as effective as possible, it helps to be stealthy. In the past, stealth meant a healthy dose of speed, combined with high altitude and a fancy paint job. But that fanatical drive to go faster and higher has given way to a more potent ambition. The ability to operate without forewarning, to seem to be invisible. A fifth-generation fighter, and perhaps the most capable air superiority weapon in the world. The F-22 Raptor is the product of 60 years of active stealth research. Designed as a successor to the F-15, arguably the most capable fighter of its generation, the Raptor was created to meet the threat from the Russian-built Su-35, giving the U.S. Air Force an air dominance fighter that was lethal, fast, but more importantly, almost impossible to detect.
Its principal differences to the F-15 were in two aspects. The first of those aspects was in observability, in stealth. Unlike the F-15, which had been optimized for its aerodynamic performance, the F-22 from the outset was optimized so that it could not be seen by the adversary.
So how do you make an aircraft invisible? You limit what's called its radar cross-section. As radar works on the principle of reflected radio waves, to not be seen requires a surface that refracts radar signals so that they don't bounce back to the source. To help achieve this, the F-22's outer shape is very clean. Great care has been taken to align all hard edges on the wing, tail, and engine inlet so that the radar return from any given point is aimed in a number of limited directions. This results in a few relatively large but narrow radar spikes that are difficult to detect and, if detected, almost impossible to track. Improvements in the design of radar-absorbing materials, or RAM, contribute to weight savings, making the F-22, while similar in size to the F-15, over a ton lighter. As aircraft speed increases, the infrared signature also increases due to the friction caused by air moving over the outer surface. And so an infrared topcoat is used on the F-22 to ensure that the radar and infrared signatures are balanced. Employing the latest turbofan engines, the F-22 cruises at unprecedented speeds without engaging afterburners, a prime source of heat and noise. And to further reduce the heat signature of the engines, the plane employs engine vectoring.
The integration of which combined the ability to reduce the infrared signature of the exhausts of those engines with the ability to vector that exhaust to increase the maneuverability of the aircraft at speed, in fact, to the point at which the aircraft had departed the normal flight envelope.
The result? The F-22 has a top speed of 2,300 kilometers per hour. While the Raptor may be one of the most technologically advanced machines on the planet, like much of the machinery of war, its design stems from the need to overcome the strategic importance of another invention. For the F-22, that invention is radar. In 1935, Hitler announced that he was breaking the First World War armistice agreement and was rearming Germany. Since the war, the rapid increase in airstrike capability, most notably the emergence of long-range bombers, was viewed as a dire threat. And so a race began to find a technology that was able to counter it. In the early 1930s, the British physicist Robert Watson Watt was working on devices for tracking thunderstorms. He had developed a system of plotting their locations using oscilloscopes. So, when in 1935, Watt suggested that he could use similar principles to track aircraft, the British government jumped at it.
Radar uses the same sort of approach that a bat uses to navigate in the dark. If you can send out some form of energy in waves, then some of those waves will bounce off, and some of them will be reflected directly back to you. And so if you can set up a system of emission and receivers that can detect those bounced radar waves, then you can pinpoint objects that you perhaps would not normally see visually.
Within weeks of Watt's claim, a test was conducted employing a BBC radio tower as the signal transmitter. Using an oscilloscope, changes in voltage bouncing back from a test aircraft emerged as a blip on a screen. And when the time delay of the signal was plotted against the calibrated scale, it pinpointed the aircraft's location. They had successfully tested radar. But the range at which the aircraft was detected was short due to the lack of transmission power and the relatively low signal frequency. Watt and his team decided that to be effective, the system had to emit waves at a very high frequency. By pushing the capacities of existing technologies, they continuously upped the range until by 1938, a working system of stations that could detect aircraft at 160 kilometers was built along the English East Coast.
The British successfully developed radar assets along the coast of the United Kingdom of Great Britain, guarding against the bomber fleets that the Luftwaffe were sending at them during the Battle of Britain.
Not that the whole process was automatic, far from it. In our admiration for radar, don't let's forget the men and women in the plotting center, for instance.
At the outbreak of hostilities, Chainholm, as it was called, consisted of just 21 stations. By war's end, there were over 100, all capable of detecting a target threat at distances of over 250 kilometers. It was the world's first early warning radar network to achieve operation.
Radar picks up all planes, but it enables you to distinguish enemy aircraft by the constant, unvarying pattern. Allied planes are equipped with apparatus that varies the oscillation.
In 1939, the British invented another device, the cavity magnetron oscillator, and its compactness was a game changer.
So subsequent to the Second World War, advances in electronics allowed radar hardware to be reduced in size and volume enough to actually put them onto aircraft. And so to this day, we continue to see radars located in the noses of combat aircraft.
Radar rapidly became an all-purpose device. One plane could spot every ship in an enemy fleet or convoy. The magic eye misses nothing.
Over 12,000 German bombers were intercepted and destroyed during World War II. Many of them with payloads that, had they been delivered, would have decimated Britain and her allies. Radar prevented that, and relatively unchanged, it has influenced every conflict since.
There's no such thing as dogfighting nowadays. I mean, you don't go Battle of Britain stuff anymore. Fighters don't see each other. Their radars see each other, but they don't.
Changing the very meaning of stealth, radar remains to this day one of the most powerful machines of war. After 2 world wars, the world slipped into a period of espionage, secrecy, and intrigue. A war in which stealth was the byword. It was the Cold War. The Cold War was a race between 2 nuclear-armed superpowers to secure political and ideological dominance. and it fueled a race for technological supremacy. But who was in the lead? Who had made the latest breakthrough? Out of this anxiety came the fastest non-rocket propelled aircraft ever built, the SR-71 Blackbird.
When the Cold War started, the U-2s were flying all over the world. During one of the missions, Francis Gary Powers, one of the U-2 pilots, was shot down. Three surface-to-air missiles fired at him. One of them came close and blew the aircraft up and blew him out of it. And so he ended up ejecting.
Powers' capture was a huge embarrassment for the United States. President Dwight D. Eisenhower reacted swiftly. He went straight to the top-secret Skunk Works division of Lockheed Martin and placed an order. He wanted a reconnaissance aircraft that could fly higher than a U-2, fly faster than a missile, and he wanted it tomorrow. It seemed impossible.
Building an aircraft that was going to fly faster and higher than the U-2 had never even been contemplated before. No aircraft had ever flown that high. No aircraft had ever flown faster than a missile. And they were given finally 20 months to build such an aircraft.
20 months to create an aircraft that could outrun a missile meant building an airplane that could travel at over 4,200 kilometers per hour, at altitudes beyond human tolerances. Immediately, the designers knew it couldn't be built from traditional metals. It needed to be fashioned from titanium. But America had limited supplies of rutile, the rare sandy soil from which titanium is extracted. The world's largest producer, ironically, was Russia.
Which caused a bit of a problem, because the Russians weren't really excited about providing titanium to the United States. So what they did was go to off-site companies, offshore companies, and they went and bought the titanium from Russia.
Initial trials found that the heat generated meant the entire aircraft expanded at speed. The expansion would have caused a smooth skin to split or curl.
So they decided that they would have to build the airplane with the ability to actually grow in flight. And so the aircraft was built to actually grow 15 inches in flight from takeoff.
Then there was the question of altitude. The Blackbird was designed to reach altitudes into the stratosphere, but at 24,500 meters, nitrogen in the blood would make the skin boil. To combat this, pilots had to breathe pure oxygen for an hour prior to a flight to expel nitrogen from their blood. While the SR-71 was designed to rely largely on altitude and speed to avoid detection, it did have significant stealth capability. The underside of the fuselage was drawn out like a small boat, which limited radar cross-section. Special radar-absorbing alloys were incorporated in sawtooth sections on the aircraft's skin, and the wings and tail fins were tilted inwards, reducing direct radar reflection.
We did have defensive systems, but again, our defensive system primarily was speed. Faster you go, and the higher you go. That was how we got away from things.
The first operational Blackbird flight was in December 1964. When it flew, it became, and it remains, the fastest jet-powered aircraft ever made, with the capability of achieving a staggering top speed of over 3,500 kilometers per hour.
Its top speed's well over Mach 3.2. The SR is the only manned airplane that's ever done that. But Mach 3 was a different world. You can't imagine how quick you can get lost at that speed if something fails. You can get really lost really quick.
32 were built, none were shot down. It was only because of the development of satellite surveillance technology and high operational costs that the SR-71 was eventually retired in 1998.
It was a cost issue. Flying the SR-71 was not cheap. You know, every estimate I've ever heard was $1 million a flight. Whether or not it really was, I don't know. But that's a lot of money.
But the lessons learned from its design proved invaluable in developing the next generation of stealth aircraft. And that aircraft was the F-117 Nighthawk. It looks like it shouldn't fly, and it deserves its nickname, the Wobblin' Goblin. But though it may be ugly, the F-117 is another cutting-edge design by two names that recur in relation to stealth aircraft: Skunk Works and Kelly Johnson. Johnson led the design of the SR-71, and the Nighthawk was one of his last projects, born after combat experience in Vietnam, where increasingly sophisticated surface-to-air missiles repeatedly downed U.S. heavy bombers.
I mean, in Vietnam, I think the tally was up to over 800 missiles fired at the SR.
The most striking thing about the Nighthawk is its faceted design, which incorporates the most sophisticated stealth thinking of its time. This meant that despite it being the same size as an F-15, it appears on radar screens the size of an average bird.
One of the main reflectors of radar is actually the fan face. And so modern stealth designs try and hide that fan face from direct view. The F-117 did this in an interesting way.
The designers at Skunk Works set the engines deep within the airframe. The inlet screened with rotatable louvers to deflect any radar signal. The Skunk Works team also added noise minimization to counter the whine that jet engines produce, making the Nighthawk unnervingly quiet.
The F-117 Nighthawk was the first production truly stealth design that had been optimized from the beginning for reduced observability, principally again in radar cross-section, but also in infrared signature.
The result is an aircraft that is quiet, all but invisible, and extremely lethal. During the early morning hours of January 17, 1991, in response to Saddam Hussein's invasion of Kuwait, a fleet of Nighthawks slipped over Baghdad unseen by Iraqi radar and neutralized 37 targets. Over the ensuing weeks, they would strike with remarkable accuracy. Less than 3% of the American aircraft in Iraq were Nighthawks, yet they accounted for 40% of all strategic targets hit. And of the 64 made, only one was ever lost in combat. But while the F-117 was deadly, it carried a limited payload of just 2 laser-guided bombs of up to 900 kilograms each. The next challenge for aircraft designers was to create a strategic weapons platform that combined stealth with massive firepower. An assessment published by the U.S. Air Force concluded that 2 of these aircraft, armed with precision weaponry, could do the job of 75 conventional aircraft. It's the B-2 Spirit, the latest generation of stealth aircraft. With a wingspan of 52 meters, the B-2 is big. And yet, when a former head of the U.S. Air Force was asked the size of its radar signature, he described it as insect category. Conceived during the Cold War to infiltrate the Soviet air defense network and attack targets with nuclear weapons, the B-2 Spirit is a high-lift, low-drag, flying wing design. Engineers have long known that flying wings have minimal radar signature. They surmised that properly shaped and constructed using advanced composite materials, they could create the ultimate penetration bomber, undetectable by radar. So almost 80% of the B-2 is constructed out of a woven carbon graphite composite. With the aid of modern supercomputers, the outer skin was shaped to deflect radar energy in a way that is far more subtle than the Nighthawk. and a new alternate high-frequency radar-absorbent coating is applied to each B-2. Its 4 turbofan engines are internally mounted and have an exhaust temperature control system to minimize thermal signature. And its weapons capability is up to a devastating 18,000 kilograms in a single payload that can include a mix of weapons, allowing it to engage up to 4 different target types on any mission. It can also carry air-to-surface missiles with ranges up to 370 kilometers, allowing it to stand off an attack from well outside a conflict zone. Capable of attack missions from altitudes above 15,000 meters, with a range of more than 11,000 kilometers unrefueled and over 18,000 kilometers with a single refueling, the Spirit has the ability to fly to any point on the globe and engage a target without ever being seen. While stealth technology is essential to modern aerial combat, on the ground, different tactics are needed. During covert operations, to take out a target from a distance requires a weapon that is both silent and deadly. Up until the end of the 19th century, armies marched into battle with soldiers in orderly lines, wearing brightly clad uniforms to aid identification. But when a small bore force, either concealed in the landscape or using skirmishing techniques, very nearly defeated the mighty British Empire in South Africa, it ushered in a new way of fighting. We know it as guerrilla warfare, a tactic that values stealth over strength. In 1898, at the Battle of San Juan Hill in Cuba, 750 Spanish regulars delayed the advance of 15,000 US troops. The Americans were armed with single-shot rifles. The Spanish were using the same rifle as the Boer in South Africa, the Mauser 93.
The first major war that the US Army had fought since the American Civil War was the Spanish-American War of 1898. In that campaign, the Americans realised that their existing rifle was obsolete and they needed to come up with a new design.
The Americans paid $200,000 to license the design from Mauser and modified it at the US Armory in Springfield. They installed adjustable iron sights at the front and rear to assist accuracy at range and reduced its barrel length by 300 millimeters, creating a hybrid long gun that could serve as both a service rifle and a carbine, making it easier to handle. And so the M1903 Springfield was born. The Springfield has a muzzle velocity above 850 meters per second, over 250 meters per second faster than its predecessor, meaning its effective range was doubled to almost 550 meters. And absolute range was increased to well over 3,000 meters. This vastly improved range of the Springfield was in part due to the decreased aerodynamic drag of the French Spitzer round, which replaced the standard bullet's rounded nose with a pointed tip. And it was smooth and reliable under the worst battlefield conditions.
The Springfield rifle was a robust design. New recruits in that vastly expanding army which the Americans created in the First World War in 1917 found it relatively easy to train and become competent in the weapon.
10 to 15 shots a minute was easily achievable, with the shooter able to fire from a safer range using smokeless powder, making them far more difficult to detect. Over 3 million were produced.
The Springfield rifle was renowned for its reliability in combat, and it was such a sound design that a sniper variant of the rifle continued to be used during the Second World War, more than 40 years after the original design was conceived.
In the hands of an expert marksman, it could reliably take out a target at over 1.5 kilometers. Add an optical sight, and what you had was a potent specialist weapon. And they gave a name to the men who operated such weapons: They called them snipers. When Germans on the Western Front began consistently claiming lives, firing across seemingly impossible distances, the Allies initially assumed it was pot luck. It wasn't until they began moving through German positions and stumbled upon rifles equipped with telescopic sights that they understood what had been happening.
Really, the story of the sniper and the sniper rifle begins in earnest in the First World War, when each of the participant nations realized they needed a much more precise version of their infantry rifle, their standard, usually bolt-action infantry rifle. And that's really what these early sniper rifles were.
The British wasted no time in emulating the German tactic, and they elevated it to a new level. They established training camps where British snipers honed their shooting skills and learned to gain advantageous positions using improvised camouflage known as ghillie suits. The underside of the ghillie suit is reinforced with heavy canvas to help pad a sniper's torso during hours or days of lying on his stomach. Camouflage netting is attached. To this is added shredded hessian and other frayed materials, as well as elements of local vegetation. Early snipers often acted alone. Many used iron sights, but optics helped realize a rifle's potential.
It meant that you didn't have to line up mechanically your front and your rear sight with your eye with the target. You just have to put the crosshairs on the target. Makes it sound simple. It's not.
But as sniping became more effective, so too did countermeasures.
We can see the classic contest between offense and defense beginning to take place. We have snipers who are highly trained, and we have the opposition, in this case the Germans, developing armor to protect themselves.
The increasingly mechanized battlefields of World War II dramatically changed military tactics on the ground. And naturally, armies across the world began to look at the potential for specialist snipers to inflict damage on more than just men.
But how on earth does the individual infantryman harness physics in a portable weapon to perhaps kill a tank? It's an extremely difficult thing to pull off, and different answers were arrived at.
Early anti-tank, or anti-material weapons as they became known, were extremely cumbersome. More mobile than an artillery piece, but only just. The British boys' anti-tank rifle of World War II was over 1.5 meters long, weighed almost 20 kilograms, and required a crew of 2 to operate.
And their story kind of peters out as tank armor just gets too thick to defeat reliably. And there's a point in the Second World War where the anti-tank rifle becomes absolutely useless, essentially.
But tanks were not the only armored vehicle on the battlefield. A weapon was still needed that could stop lighter armor. And to make that weapon difficult to detect meant reducing its weight, suppressing its noise, and taming the incredible recoil forces it would generate. In the 1980s, a weapon arrived that filled all those criteria: the Barrett M82. The Barrett M82 sniper rifle is the benchmark large-caliber anti-material rifle that revolutionized the field of military sniping. Referred to as a multi-role weapon system, the M82 has an effective range of over 1,800 meters. But anti-personnel work is not the weapon's primary purpose. It is more commonly deployed against hard targets, like buildings, armored vehicles, parked aircraft, and communication systems. To create a weapon of this power and portability first required a reduction in weight.
There's a constant quest to lighten all weapons, but especially weapons that tend to be very heavy and cumbersome, simply because you can use them much more flexibly.
To achieve this, the Barrett's barrel is fluted, a design that also improves heat dissipation. Elements of the stock are constructed using lightweight plastics. But what's truly unique about the Barrett is its buffer system. The entire barrel is set on rails and travels back 3.8 centimeters against springs, a revolutionary development that allows it to be fired from the shoulder, unaided by tripod bracing.
The Barrett's recoil-operated system sacrifices a little accuracy for low recoil, which is very important when firing an extremely powerful cartridge like the 50 Browning machine gun cartridge.
All of this allows the M82 to deliver previously unheard of levels of energy and distance with low observability. A sniper rifle capable of putting a 50 caliber round through the block of a truck engine from over a kilometer away. But the effectiveness of a modern sniper is enhanced not just by the rifles they use. Advances in glass manufacture have led to massive increases in standard magnification, and the increasing use of transparent polymers has greatly improved the light transmission of modern scopes. Such scopes, fitted to rifles like the M110 sniper system, equip the sniper with what is a true precision weapon. With the M110, that precision begins with the barrel.
If you think about the microscopic imperfections in a rifle barrel, every one of those can upset the bullet very, very slightly. And so if you're able to go down to that microscopic level, and if you're able to remove all of those imperfections, in theory, you will have an ultra-precise bore, something that they couldn't have dreamed of in 1918.
The M110's 50-centimeter chrome-plated barrel is made from the highest quality modern steel with greatly reduced imperfections. It also features what is called 5R rifling.
The important thing with sniper rifles is that you minimize barrel vibration when you fire the projectile, and that is so important for accuracy, because as you fire the projectile, the barrel may have a tendency to vibrate. And if you minimize that amount of vibration, then that's going to improve the level of accuracy.
5R rifling reduces projectile damage, ensuring the projectile remains more uniform. And a more uniform projectile translates into less vibration and improved accuracy. The changing nature of battle revealed the limited engagement capabilities of traditional single-shot bolt-action rifles. This was particularly problematic in urban Iraq during the US-led invasion, where non-repeating sniper rifles became a tactical liability. With a larger 20-round magazine, a sniper carrying an M110 who finds themselves under threat can easily switch the weapon into automatic mode, allowing them to fight their way through to safety. 2 weapons in one, and yet extremely accurate. In the hands of a skilled sniper, the M110 can group 10 shots fired rapidly over a distance of more than 90 meters within a radius of less than 1.5 centimeters. Stealth on land relies on silence, camouflage, and guile. But in the wide expanse of the open ocean, it's much more difficult to hide. At sea, the stealthiest place from which you can do damage to enemy shipping is not from the surface, but below it. On the morning of the 5th of September 1914, HMS Pathfinder, the lead ship of the British Pathfinder class of cruisers, was spotted by the German U-boat U-21. Stalking her at periscope depth, U-21 fired a single 50-centimeter torpedo at a range of 600 meters. Within minutes, she was lost. It was the first sinking by a U-boat in World War I. Thousands more were to follow.
Many naval people in the beginning of the 20th century regarded the submarine as a really underhanded weapon, a weapon to be used by the coward. Yet the ability to approach unseen and to wreak damage revolutionized warfare at sea.
The undersea boat, or the U-boat as they became known, was more a submersible ship than a submarine as we think of them today.
They were fast on the surface. They could do something like 17 knots, but dived only about 7. So they would do most of their hunting on the surface and then dive for the attack.
There were many Allied submarines, but what made the U-boat superior and gave it its tactical edge was its diesel-electric propulsion system. The Germans had long understood the value of diesel engines and led the world in their design. In 1915, a reliable 4-stroke diesel engine was produced that far outstripped the performance of any Allied equivalent. The U-boat could keep pace with most merchant ships of the day, with a range that allowed them to choose their time to attack. Using electric motors to get them within range, they would surface and either engage with deck-mounted guns or torpedoes. U-boats quickly became the most prolific killers on the seas. While in 1914, German surface ships sank 55 ships, compared to only 3 by U-boats, the following year, this was reversed, with U-boats sinking 396 Allied ships, compared to only 23 by surface craft. Between 1914 and 1918, nearly 10,000 ships, thousands of planes and dirigibles, and more than 100,000 mines were deployed to combat a U-boat fleet which totaled just 340 submarines. The Allies may have eventually won the war on land, but the success of the U-boat campaign underscored how important and devastating submarine warfare could be, a lesson that was repeated to an almost decisive effect in the Second World War. The Type 7 U-boat was the workhorse of the German submarine fleet during World War II.
They were designed really for service in the North Sea and in the western approaches to Europe. They were very effective in their job of trying to cut off sea communications to Britain. And there were more Type 7 U-boats built than of any other submarine ever.
Over 700, in fact. But the Type 7 was more an evolution rather than a revolution.
They were quite a small submarine, and in terms of their technology, they were little changed from the submarines of World War I, with similar size and similar capability.
Additions included large external tanks holding 33 tons of extra fuel, which increased range, and supercharged diesel engines gave a slight increase in overall speed. Improvements in the efficiency of the electric motors extended the time they could remain submerged. And they carried an increased load of torpedoes. But it was improvements in shipboard communications that was their deadliest asset. It allowed German submarines to hunt in groups that became known as wolf packs.
Well, wolf pack was a group of submarines operating together. They could be very, very effective because they could surround a convoy and attack it from multiple directions all at once.
Undoubtedly, one of the most formidable assets of the Axis powers in the present phase of the war is the U-boat.
Initially, they were very effective in disrupting supplies to Britain. In the first 6 months of the Second World War, Britain lost more than 300 ships, while the Germans lost just 17 submarines. And as the war spread, with America's entry, so too did the Battle of the Atlantic.
The U-boat campaign, certain to be intensified, is Hitler's greatest hope of staving off defeat. He has hundreds of U-boats at sea now. He'll undoubtedly have more. The answer is to destroy them.
But luck began to run out, as submarine countermeasures evolved.
Allied air patrols over the North Atlantic became more effective, and radar became more available, which made them very vulnerable. If you want to combat an air attack on a submarine, you have to stay well submerged and keep out of the way. And that was difficult because, like many early submarines, the Type 7s were basically a surface ship which could dive.
The Germans realized they needed a way to carry out such operations while remaining submerged. And the answer to that was the snorkel.
The Germans adopted the Dutch snorkel and retrofitted it to quite a number of the Type 7 submarines, which made them much less vulnerable.
Although the snorkel improved the odds, improvements in detection technology, combined with the development of specialist ships to hunt and destroy U-boats, meant that they were no longer the supreme stealth weapon they had been. In fact, by 1945, U-boat losses were routinely 30 per month, and in April of that year, they exceeded 50.
Not so long ago, the Battle of the Atlantic was the most critical factor in the war. Now, convoy after convoy, all strongly escorted, crosses the Western Ocean virtually unmolested in comparison with those days of crisis. When U-boats appear, it's they who are hunted now.
But the end of the war and the birth of the nuclear age unlocked a power source that would redefine submarines and restore their place as perhaps the most feared of all stealth weapons on the planet.
After World War II, the British put most of their effort into commercial nuclear development. But in 1947, Westinghouse were authorized by the US government to develop a nuclear reactor which was capable of being fitted into a submarine.
That reactor was fitted to a submarine named the USS Nautilus, and it was revolutionary. Launched in 1955, the Nautilus was able to achieve a submerged speed of 23 knots, and her hull could withstand pressures at depths over 200 meters.
The important thing about the nuclear submarine is it can remain submerged, really, for a very long period of time. And the submarine's endurance is really determined not by the fuel or the battery capacity, but by the amount of food you can carry and the endurance of the crew. And that was a major revolution in submarine design.
From 1955 to 1957, the Nautilus was put through a series of trials. Trials which showed her revolutionary teardrop-shaped hull would allow her to match speed with those on the surface. No longer would the submarine be a fast surface ship that temporarily submerged, but a fast submersible ship.
I think the most important thing about Nautilus is that she proved the value of nuclear power in submarines. By the mid-1950s, the United States had stopped building conventional diesel-electric submarines.
To prove the supremacy of nuclear power, on the 1st of August 1958, the Nautilus submerged near Alaska and surfaced 96 hours later northeast of Greenland, having completed the first submerged voyage under the North Pole.
But all went without a hitch. Nautilus passed safely on her route right under the pole. A tremendous achievement and a moment of relief, I should think, for all on board when she surfaced.
The Nautilus had demonstrated that she was at the cutting edge of stealth technology. But during the Cold War, as the Soviets developed their own nuclear submarines, the US was compelled to stay ahead. '62 Los Angeles-class submarines, the largest group of vessels constructed for the United States Navy during the Cold War, were specifically designed to counter the Soviet submarines that the Americans believed would, in the event of hostilities, target the heart of their Navy, the carrier groups. Much of the information about the Los Angeles class is classified. We know that it is capable of 20 knots on the surface, and its reported top speed while submerged is 33 knots. If continuously operated, its propulsion plant requires refueling just once every 9 years. The Los Angeles-class submarines are armed with a mix of both land attack and anti-ship versions of the Tomahawk missile, complemented by 25 torpedo tube-launched missiles, including the Harpoon anti-ship missile.
Submarines, of course, are a pressure vessel. They consist of several major components. The most principal one, of course, is the pressure hull. And the more cylindrical that is, the better it withstands pressure.
The deeper you go, the more difficult you are to detect. And depth means pressure. Increased power from nuclear reactors allows submarine hulls to be thicker. But a hull's strength is also measured by how elastic it can be under pressure. And this yield strength requires special steel alloys. Although the operating depths of submarines are secret, their crush depth can be calculated if you know what they're made from. The Los Angeles class have pressure hulls made with HY80, a nickel chrome alloy with incredible strength and elasticity. This puts their crush depth somewhere around 600 meters. Deep and stealthy. But stealth at sea is no longer the sole domain of the submarine. At almost 183 meters, the largest destroyer ever commissioned for the U.S. Navy, the Zumwalt-class guided missile destroyer, is as close as any ship has come to being invisible.
They're big ships. They're something like 15,000 tons, so to call them a destroyer is something of a misnomer. But it's a very stealthy ship, which was difficult to find with radar.
To make a ship of this size difficult to detect has required a complete shift in naval design thinking and the application of lessons learned from aviation stealth technology, beginning with the shape.
The structure is designed with a lot of tumble home so that the upper deck is narrower than at the waterline.
The opposite to that of traditional vessels, resulting in a significant reduction in its radar cross-section. Like the F-22, the weapon systems are discrete. The decks are clear with virtually no sharp lines that could return a radar signal to its source. On a typical warship, you see an arrangement of spinning dishes and antennas sitting atop a high-profile mast. The Zumwalt's deckhouse is a clean, angled structure, straight out of the F-117 design book. Its array of radar sensors and communications hardware is integrated directly into the deckhouse skin, which is built of composites, much like the B-2. By incorporating these lessons, designers have managed to give the Zumwalt an almost 15,000-ton heavily armed warship capable of 36 knots, a radar cross-section the size of a fishing boat. Improvements in stealth design are continually being counterbalanced by the ongoing development of detection methods. The Zumwalt represents another beginning in the race to appear invisible. And science continues to push the boundaries of what seems possible. Current studies involve cloaking aircraft in plasma shields, fields of ionized gases that absorb all radar signals, and experiments with technologies that bend light waves to render objects, or even people, invisible to the naked eye. It seems that if science fiction can think of it, militaries will try to make it a reality. From concrete bunkers to vast underground railways, machine guns capable of firing thousands of rounds a minute, to precision lasers able to instantly neutralize a threat, intercept fighters to armor plating, the machinery of war with the ability to attack are almost worthless without the machines that protect. Without defense, there would be no battle, only surrender. This is the story of defense. When flimsy aircraft first appeared above the battlefields of World War I, few could have imagined the influence they would have on the shape of war. In less than 20 years, they went from curiosities to weapons of incredible destructive force. World War II had initiated a new chapter in aerial warfare. And to combat that threat, nations on both sides looked to ways to defend their airspace, in the air and from the ground. Amongst the German arsenal of anti-aircraft weapons were a variety of small-caliber light artillery pieces for low-level attacks. For aircraft operating at higher altitudes, it had developed a weapon that became simply known as the 88. A supreme anti-aircraft gun that had two aims.
The first was to keep the bombers high, rather than letting the bombers come lower and be more accurate. And the second was to kill bombers. There were belts of 88s, both on the approaches to major German cities, but also along the coast, so that the Allied bombers had to cross literally bands of heavy and accurate anti-aircraft fire to approach the cities of the Reich to bomb them.
The secret of the 88's power lay first of all in its caliber. At 88 millimeters, it was a very large exploding shell fired with a timer that meant it would detonate at a set altitude. But it also had a very long barrel, which gave it a very high muzzle velocity, and with it, the ability to fire a shell to an altitude of more than 7,500 meters. Well within the target range for most bombers. But what really set the 88 apart was its rate of fire.
So instead of having to load the shell and sight the gun each time, the Krupp automatic loading meant that it could fire 15 to 20 shots a minute, which meant that you could literally put up a barrage. So a battery of 4 guns could put up 80 shells in the course of a minute, which is a wall of steel which the aircraft have to fly through. It's the technical capacity of the German armaments engineers in the 1930s that are actually defending the Reich into the 1940s.
Over 20,000 German 88s were produced, including variants and modifications derived from lessons learned in action.
The German 88mm gun is one of the most extraordinary artillery weapons of all time. Every nation developed a heavy anti-aircraft weapon, and none of them were as good as the 88. And the British and the Americans never had a gun to match the 88's capacities.
While the 88 may have been a supreme weapon in its time, the development of attacking machines waits for no weapon. The character of war at sea has produced new threats that demand ever more sophisticated means of protection. On the 2nd of April 1982, Argentine forces mounted amphibious landings off the British colony of the Falkland Islands. The British and the Argentine forces squared off in what was essentially a war at sea. What became immediately obvious to both sides was that in maritime warfare, things had changed. And the key to that change was the introduction of the anti-ship missile.
Ships were incredibly vulnerable to these systems. If you couldn't shoot down the aircraft or you couldn't take out the host ship before the anti-ship missile was launched, you were in a sense helpless.
While militaries around the world had known of the dangers of anti-ship missiles, the loss of 6 British warships during the Falklands conflict offered the first real-world example of their potential destructiveness. What was needed to combat that threat was a last-ditch defense system. And for a last-ditch defense, you need something that's incredibly fast and responsive. A system capable of destroying an inbound missile in flight on the last line. The Phalanx Sea Whiz is such a weapon. The Phalanx is an automated close-in weapon system built around the Vulcan 6-barrel Gatling autocannon. In use since the late 1950s on U.S. attack aircraft, the Vulcan fires heavy 20mm shells at the astonishing rate of 4,500 rounds per minute. Housed in an entirely self-contained turreted mounting, the gun is linked to an automated radar fire control system that enables it to automatically seek, detect, track, and engage incoming targets. A task it can perform entirely autonomously.
It doesn't require a human in the loop. It will simply pick up the target, fire at it, and destroy it. And because it has this enormous rate of fire, it's effective against things like incoming anti-ship missiles, but even large artillery shells.
The advantages of an autonomous system are many, but the most significant is in targeting and response times.
Taking a human out of the loop means it can react much quicker than a human being could, and it is very, very effective. It doesn't get worried, it doesn't get concerned, it doesn't get tired. If the systems work as we hope that they will someday work, it is potentially more discriminate and more proportional than a human being.
Where the Phalanx's autocannon effectively shreds the inbound projectile, the integration of the Phalanx's control system with a commercial-grade laser could lead to a different future for air defense weaponry. To the untrained eye, it looks like a telescope, and the operators sitting behind a screen look as though they're playing a video game. But this is no game. Lasers are at last entering military service, and warfare will never be the same. It is the laser weapon system, or LAWS.
The first idea of lasers came from Einstein in 1913. Einstein predicted that we could generate light not with multiple frequencies like in a lamp, but with a single frequency, and we could order light so it could go in the same direction.
In theory, laser weapons target an object with a train of brief pulses of high-intensity light energy. The heat generated causes rapid evaporation and expansion of the surface, creating shock waves that damage the object. It's taken over 50 years to make them practical battlefield weapons, overcoming numerous technological hurdles along the way, the biggest being the conversion of energy into the actual beam emitted. Early lasers could only convert 10% of the total power input into light energy, which meant that to create an effective laser weapon, a huge power source was required. Using the latest technology in optics, LAWS projects an infrared beam from a solid-state array that converts 50% of available energy. And when its beam is tuned to high output, it can affect the structural integrity of aircraft, burn holes in the hulls of small boats, heat artillery shells in midair, causing them to explode, or heat storage containers at a fuel dump until the fuel ignites. And tests aboard the USS Ponce in 2014 have proved it works. Among the advantages of a laser, compared to a projectile weapon, is that it requires no projectile. There is no need to manufacture, transport, or store munitions. It is solely reliant on a power source, which makes each shot virtually cost-free.
It's much cheaper than a missile, for example. If you fire a missile, it may cost $100,000 or $1 million. And with a laser shot, it can cost like $2 or $1.
Lasers may never totally replace other weapons. An international agreement means they can't be used to target individual people. Still, for targeting practically everything else, the time of lasers is finally coming. It's warfare at the speed of light.
We may well see near-future wars in which autonomous robot drone swarms are attacking a target and being shot down by lasers. It sounds like science fiction, but it's really happening.
Fighter aircraft have always captured the public attention. In World War I, dogfights between biplanes sought to control the skies so that just one side could see the battlefield to direct their artillery. But in World War II, as the skies of Europe and Asia filled with bombers targeting cities, they took on a much more serious role. Anti-aircraft weapons can only do so much in defense of those on the ground. And sometimes, the only way to defend is to take the fight to the skies. On the 16th of July, 1940, Adolf Hitler ordered the preparation of Operation Sea Lion, a potential airborne and amphibious assault on Britain that would come once the Luftwaffe had established air superiority over the UK. And so the famous Battle of Britain began. And standing between the Luftwaffe and victory were two aircraft, one of which was Britain's first monoplane fighter, the Hawker Hurricane, an aircraft designed in the mid-1930s.
At the time, the whole RAF was still flying biplanes. Around that time, the Messerschmitt 109 came into being. Single-engine, stress-skin monoplane fighter, heavily armed, quite fast, and the RAF said, well, we don't have anything to match it. So they put forward a request to British industry, and the Hawker Hurricane and the Submarine Spitfire were the initial results of that.
The Hawker Hurricane was in many ways a transitional aircraft, constructed using a mix of old and new techniques. A steel tube fuselage was bolted together, over which were fitted wooden stringers that gave the aircraft its streamlined shape. The wing structure was forged of aluminium, but unlike the ME-109, which had a modern aluminium stress skin, the Hurricane was covered in fabric. And that fabric skin would prove to be one of the Hurricane's strengths.
The Hurricane was easier to turn around than a Spitfire, particularly battle damage, because more often than not, you just throw a fabric patch over a bullet hole and send it out again.
While the Hurricane was an impressive fighter, it could not have won the Battle of Britain alone. The German Messerschmitt 109 was simply too fast. Hurricanes, supreme against incoming bombers, needed to fight alongside an aircraft that could match the capabilities of their Messerschmitt escort. That aircraft is perhaps the best remembered fighter of World War II, the Supermarine Spitfire. Where the Hurricane had been something of a compromise between old and new, the Spitfire heralded an all-new method of building fighter aircraft. It was an all-metal design with a monocoque frame and aluminium alloy stress skin covering the outer surfaces, making the Spitfire incredibly light and streamlined, contributing to its legendary maneuverability. It also made it difficult at first to build with the industry required to manufacture and work metal airframes, and the particular manufacturing issues surrounding the famous elliptical wing, a complicated design intended to reduce drag and increase aerodynamic performance. That wing proved revolutionary, and along with the Rolls-Royce engines, it gave the Spitfire astounding aerodynamic capability, and perhaps more importantly, speed.
The role of the Spitfire was to take on the fighters. When the Germans sent across their Heinkel 111s and Junkers 88s, they were escorted by Messerschmitt 109s and 110s. It was the Spitfire's job to take on those two aircraft to allow the Hurricanes in to take out the bombers.
Technically, it had a slight edge on the Messerschmitt, but the contest was close run and often came down to the skill of opposing pilots. The Spitfire may be better remembered than the Hurricane. The two aircraft worked very much together.
Without the Hurricane backing up the Spitfires, and the Spitfires looking out for the Hurricanes, the Battle of Britain would have ended very differently.
When the Spitfire and the Messerschmitt did battle in the skies above Britain, they were among the fastest aircraft of their time. But as the war came to a close, jet engines began to roar. And within less than 5 years, in the skies over Korea, a new jet aircraft dominated, the technologically advanced MiG-15. Developed in 1947 to intercept bombers, the MiG-15 design drew on valuable lessons learned from World War II. The first thing acknowledged was that it had to be fast enough to intercept targets before they could enter friendly airspace. To achieve this, the Russians copied and improved on British Rolls-Royce jet engines sold to them at the end of the war. The power of the new jet technology was then combined with a new wing design to give it unrivaled speed.
Swept wings allow for a similar lift capability but less drag. Instead of trying to push a plank through the air horizontally, if you sweep it, it's easier to move through the air.
This combination of two new ideas made for astounding performance gains over earlier aircraft. The MiG streaked through the sky at close to 1,100 kilometers per hour. Its rate of climb was 3,000 meters per minute, almost twice as fast as the first-generation straight-wing jet fighters like the Gloucester Meteors that were sent to combat. And where the MiG also shone was in armament.
Fortunately, the plane was delivered to the Air Force combat loaded, so armament tests could be made.
The Russians had learned during World War II that aircraft equipped with machine guns simply couldn't inflict sufficient damage to cripple large aircraft. And so the MiG-15s were equipped with one 1.45-inch and two 9-inch cannons. As a result, when MiG-15s began mauling B-29 superfortresses, the effect was as startling to the Americans as it was devastating. The U.S., which until the MiG's introduction had been able to bomb with impunity, was forced to abandon daylight raids since their bomber escorts, straight-winged F-80 and F-84 fighters, were completely outclassed. With UN air superiority on the brink of collapse and the Korean Peninsula at risk, the United States deployed the only aircraft which could hope to stop the MiG, the untried F-86 Sabre. The MiG-15, though incredibly capable, was a jet aircraft that had been built in a similar way to aircraft from World War II. Still very much a mechanical airplane, in that all of the control surfaces were operated by wires and pulleys connected to the flight stick. The F-86 Sabre, by contrast, was an all-new aircraft design that attempted to apply the very latest developments in aerodynamics, avionics, and jet engine technology in a single package.
It's the first American aeroplane to have full powered flight controls. So the ailerons and elevators are controlled hydraulically via electrical signals and multitude of valves and switches, and it's a very complicated system but very advanced for its time. The main role of the Sabre was to combat the MiG-15s, and they were fairly evenly matched depending on the altitude that the fight took place. At lower altitudes, the MiG was more capable. It was a more aerobatic aeroplane at low altitude.
Despite the Sabre's disadvantage at low altitude, the two aircraft proved to be fairly evenly matched in performance. The Sabre was slightly quicker, and although it couldn't fly as high or climb quite as quickly as its Soviet-made opponent, it could dive faster, was more aerodynamically stable, and importantly, it was fitted with the latest radar targeting system that automatically acquired enemy aircraft during high-speed dogfights. A total of 224 Sabres were lost, of which about 100 were the result of aerial combat. But they destroyed 566 MiGs, although the disparity between the two was lessened when the MiG was in the hands of an experienced Russian pilot. Regardless, and despite looking outwardly similar, it was the technologically superior Sabres which won the day. And just as agile aircraft are built to attack and defend bombers in the sky, on the sea, fast, high-powered vessels defend convoys and less mobile maritime assets. Although these heavily armed protectors aren't called fighters, they're called destroyers. At the beginning of the 20th century, navies across the world had developed a fascination with torpedoes, which were considered the most feared weapons in maritime warfare. Every navy in the world had a fleet of torpedo boats, and the bigger navies a corresponding fleet of small, fast torpedo boat destroyers. In World War I, the war at sea very quickly evolved in a way that hadn't been expected. German submarines armed with torpedoes posed a constant threat, and a need arose for fast, well-armed vessels to protect the fleet and merchant ships from the menace. Vessels that could operate in heavy seas. In 1916, the British commissioned a design for a much larger torpedo boat destroyer that could fill the role and lead the existing destroyer fleet. The result was the V and W class. The principal characteristic of the early destroyer was speed, and the V and W class were an evolution of those designs. Long at 95 meters and narrow with a beam of just 9 meters. Their compact hull design featured a higher freeboard than previous, which gave them much greater ability in heavy seas. And with a top speed of 34 knots, they were fast and heavily armed.
They introduced a number of features, not the least of which was the different arrangement of the guns. 2 guns forward, one superimposed above the other, and 2 guns aft, providing the familiar A and B and X and Y turret configuration, which proved to be very, very successful.
Built between 1916 and 1924, 67 of the ships were completed, many going on to serve in World War II.
Became a style pattern, so to speak, for British destroyer design for the best part of a quarter of a century.
But threats evolve, requiring defenses to do the same.
The World War I concept of a long line of destroyers steaming at 30 knots heading towards the enemy battle fleet with the torpedo tubes trained over the side to fire torpedoes and sink the battleships is long gone. That's 100 years ago. That's a different style of warfare.
In fact, the style of warfare has changed to the point where today there are no battleships and very few battle cruisers, as the most destructive ships of the naval line were once called. Today, that frontline role is undertaken by destroyers. And for the United States, since the late 1980s, that role has been fulfilled by one design: the Arleigh Burke class. Just like the destroyers of old, the Arleigh Burke are long at over 150 meters, narrow, have a shallow draft, and a top speed in excess of 30 knots. But that is where the similarities end.
It is a ship which, in many ways, is far more capable than a World War II cruiser. It is able to strike land targets at some distance. It can engage other ships. It can engage aircraft. It is able to control large areas of sea with modern fire control systems, and they're a powerful warship.
Ships like the Arleigh Burke class are referred to as multi-mission destroyers, taking on the role of both defender and attacker. With Tomahawk cruise missiles for attacks on land-based targets, Harpoon anti-ship missiles, acoustic homing torpedoes for anti-submarine duties, a suite of short, medium, and long-range missiles designed to intercept enemy ballistic missiles at any stage of their trajectory, and the latest surface-to-air weapons, the Arleigh Burke class is an incredibly capable weapons platform, with a level of firepower that crews of the V and W class destroyer would have found unimaginable. But the capacity to attack is nothing without the ability to defend. The Arleigh Burkes incorporate elements of stealth design in the angled hull and the tripod mainmast, which make them more difficult to detect by anti-ship missiles. This is combined with the latest air and missile defense systems that can detect a golf ball-sized target as far out as 166 kilometers, giving it ample time to engage countermeasures. Should something get through, a suite of close-in weapons, including the Phalanx Sea Whiz, stand guard on deck. And an air filtration system makes the Arleigh Burkes the first U.S. warships designed to endure in the event of a nuclear, biological, or chemical war. If the Arleigh Burke class is the ultimate expression of the old adage, the best form of defense is attack, then land-based defensive structures would represent the directly opposing view, one that implies that the best form of defense is attrition. With the weaponry of the 20th century evolving at a rate that in many ways outpaced tactics, and with mechanization increasing the speed of battlefield advances in World War II, nations turned to the age-old strategy of permanent or temporary structures designed to slow an enemy and defend positions. Structures that in World War I had resulted in utter carnage. The last line of German defense in World War I was a 160-kilometer stretch of concrete bunkers and pillboxes in front of which stretched tracks of barbed wire that were at times 91 meters deep. It was called the Hindenburg Line. Under intense pressure, the Hindenburg Line had failed. But it had provided enough resistance to encourage the French, alarmed at the possibility of renewed German aggression, to build their own defensive wall in 1930. The Maginot Line.
Obviously, the French knew, especially from World War I, that you need a defensive position, a defensive posture. So the Maginot Line was a series of interconnecting pillboxes. You had tank ditches, you had physical obstacles in the way to try and deter somebody from coming through.
The Maginot Line was not a single continuous structure. Instead, it was composed of over 500 separate buildings, each arranged according to a detailed plan. The key units were 50 large forts, or ouvrages, which were located within 14 kilometers of each other, along the borders with Germany and Italy. These forts were often connected using reinforced underground tunnels and were placed near enough to each other to provide interlocking fields of fire. The surface areas of these vast bases were protected by steel reinforced concrete, which was up to 3.5 meters thick, a depth capable of withstanding multiple direct hits from the largest artillery. They were fitted with steel turrets, domes that nestled on the ground when under attack, and elevated for firing. In theory, the Maginot Line was capable of creating a massive continuous line of fire that should have devastated any attack. However, it had one major failing. It was not mobile, and warfare had changed. Mobility had caught up with firepower. And when in May 1940, the German army attacked through Belgium, as it had in World War I, and crossed the supposedly impenetrable forests in the Ardennes, the closest the thousands of French soldiers manning the Maginot Line came to seeing action was watching unchallenged waves of German bombers flying over it. In 1942, there was only one way to attack Europe en masse, and that was by sea. And with Germany in almost total control of the continent, Hitler decided to keep it that way. With a workforce of close to 1 million, the Germans began construction on what would be the largest network of fortresses built in the 20th century, the Atlantic Wall. A formidable collection of an estimated 15,000 reinforced concrete bunkers, stretching across the Belgian and French coasts from the Norwegian to the Spanish border. The Atlantic Wall consumed more than 1 million tons of steel and 17 million cubic meters of concrete. In all, there were 70 batteries along the Danish coastline, with 293 large caliber guns, 225 batteries in Norway, with over 1,000, and 343 batteries along the French coast, which included 1,348 heavy weapons and an assortment of anti-tank and anti-aircraft positions, machine gun posts, munitions storage areas, and bunkers housing supplies and power generation equipment. The Atlantic Wall was the first line of Fortress Europa, as Hitler called it, and the 630-kilometer West Wall, or as it was better known, the Siegfried Line, the last. Built between 1938 and 1940, the Siegfried Line incorporated more than 18,000 bunkers, pillboxes, and tunnels, stretching along the French border from the Netherlands to Switzerland. Designed to slow an offensive while reserves are brought up, the Germans knew the speed of tanks posed the greatest threat. And so a vast network of tank traps were central to the line's design.
So generally you've got to have a trench that's wide enough to trap the tanks where they are so they can't break through. Then you've got tetrahedrons, so big concrete triangles, so tanks can't climb over them basically, because if they do, they get stuck on the point and lose traction.
And like the barbed wire of World War I that was often laid to funnel troops to their death, the tank traps were designed to lure tanks to their destruction. But defensive walls can be breached with enough concentrated manpower in one location. And once breached, they can't be moved. The Atlantic Wall was pierced when 156,000 Allied troops landed on the beaches at Normandy. And thousands of ships and aircraft threw their might into General Eisenhower's Great Crusade. It marked the beginning of the end of Fortress Europa. And like the barbed wire of World War I, the Hindenburg Line, and the Atlantic Wall before it, the Siegfried Line offered some respite to retreating German troops, but eventually buckled under the weight of the Allied advance. Like its predecessors, it fell victim to the mobility of modern warfare and was overrun in early 1945. And with it, the Third Reich fell. If the enduring image of the First World War is a misery of wire and mud, it was partly made so by a revolution in armaments. Trenches and barbed wire will slow in advance, but waves of men can only be completely stopped by firepower. Hiram Maxim was a man of great curiosity, an inventor of a diverse range of items. One of his creations would make him a wealthy man and change the course of history. The story goes that Maxim was talking with a friend in Europe who told him to forget his chemistry and electricity. If you want to make a pile of money, invent something that will enable these Europeans to cut each other's throats with greater facility. And then he had a chance experience.
So the story went that Maxim fired the M1903 Springfield rifle and was struck, literally, by the recoil. And it occurred to him that he could harness that power.
Maxim designed a system that took the force of the gun's recoil to operate it automatically by simply using the explosive energy from the firing of a projectile that would otherwise go into a rifleman's shoulder and have it drive the working parts backwards. Maxim conceived the idea of what we now know to be the machine gun.
Later, Maxim's company was bought by the Vickers Company, which was a major British armaments company. Vickers made some modifications to the design to make it more efficient, and in 1912 produced what we know as the Vickers machine gun.
What they produced was a weapon that could continuously fire an extraordinary 450 rounds per minute. But that rapid firing generated extreme levels of heat.
One of the really distinctive features of the Maxim series of guns, others as well, is the big blocky barrel section, if you like. Well, the barrel is actually very slim, and the barrel sits inside what is actually a water jacket.
The jacket around the main barrel contained 3.7 liters of water that had to be kept up to the weapon to ensure that it didn't overheat. In the stalemate that was the Western Front, it was the perfect defensive weapon.
Where you've got a fixed machine gun and you're able to dominate the landscape in front of you. The classic movie image of swinging back and forth this weapon that's utterly devastating. The Devil's Paintbrush is one of the nicknames for Maxim's gun later on.
The Vickers machine gun was such an efficient design, it remained in service in some fashion until the 1960s. But the need for a constant water supply meant it took as many as 6 men to operate it. With increasingly mobile attacking forces, unreinforced static defense placements quickly became tactically obsolete. Modern warfare demanded defensive mobility to meet an attacker anywhere on fronts of increasing scope. The Vickers, with its water cooling system, simply couldn't keep pace. When Hiram Maxim invented his automatic machine gun, it replaced another weapon that had gained only modest favor amongst the militaries of the late 1800s. The Gatling gun.
This is not a machine gun that, as we would describe it today, but we would call it a manually operated machine gun with a rotating cluster of barrels and some sort of feed device for the ammunition sitting on top. It's a machine, an engine that fires more than one shot, in this case by turning a crank.
Gatling's 1862 invention had failed to capture the hearts of the Army in its day. But when modern electronics and hydraulics were applied to replace the manual crank handle, and it was given modern armor-piercing rounds, it became the ultimate expression of the original, a 7-barrel machine cannon of devastating power. Like so many modern weapons, the GAU-8 was designed in 1970 with a particular Cold War what-if scenario in mind. In this case, it was, what if the Soviet tank forces just happened to come over the horizon? The Americans decided they would need a fast, highly mobile anti-tank weapon to defend against the possibility. And when the GAU-8 was found to be effective against heavy armor, it was given its own high-speed delivery mechanism. The Fairchild Republic A-10 Thunderbolt II, commonly referred to as the Warthog.
These things would scream in overhead and just destroy the armor, limiting the need to engage them tank to tank or to use anti-tank weapons, infantry anti-tank weapons. In practice, of course, the Cold War did not go hot. As an anti-tank tool, it kind of fell by the wayside.
And the GAU-8, along with the Warthog, might have passed into the footnotes of history like the Gatling gun had it not been for the Gulf War, where it was used against Iraqi armor with devastating effect. Very quickly, it was realized it could be an immensely capable close air support platform.
Not only will it penetrate tremendous amounts of armor or cover or anything you put in front of it, the energy being put forth by this is just so tremendous.
The Avenger has an astronomical maximum firing rate of up to 4,200 rounds per minute. That's roughly 70 rounds a second. And its armor-piercing rounds are lethal.
So it's projecting these huge 30mm in diameter shells, which are about yay long, and contain an immense amount of explosive potential. Everyone who's been in service anywhere near it loves the thing, and anyone who's faced it, I imagine, has feared it.
The GAU-8 Avenger is the pinnacle in the development of the machine gun. A line drawn from the defensive trench emplacements of World War I to close air support actions. And like all machines of war, they continue to adapt and evolve. The most fragile piece of equipment on any battlefield is the soldier. And for centuries, militaries have sought ways of protecting that asset. Body armor is nothing new. We are all familiar with the suits of armor worn by the knights of the Middle Ages. In the 20th century, the idea of offering protection to the enlisted man began with the issuing of simple steel helmets in World War I. But there's only so much you can get under a steel helmet. In World War II, air war resulted in huge losses of aircrew, who were quite literally sitting ducks for anti-aircraft fire. From a growing need to defend the undefended came the genesis of what we now call the bulletproof vest.
There was something called a flak jacket, and that was kind of the original name for a bulletproof vest. Aircrew used to wear these nylon vests which had these little 2-inch steel plates which were interwoven, and they would provide protection, as the name implies, from the flak, from the fragments from anti-aircraft munitions.
But they were bulky and extremely heavy. A problem solved in the early 70s with the discovery of Kevlar, a lightweight polymer 5 times stronger by weight than steel.
Over time, ballistic protection that was being offered to troops was getting better and better, and at the same time, the burden to troops was becoming less. So the vests themselves were getting lighter.
More protection, less weight. And as that evolution has continued, the bulletproof vest has been renamed. The Improved Outer Tactical Vest, or IOTV, is the very latest in troop protection. A medium-sized IOTV weighs 1.6 kilograms, down from 10 kilograms for a World War II flak jacket. Fully equipped, it has soft armor panel inserts, 4 silicon carbide ballistic plate inserts front, side, and rear, and collar and groin protectors. It is also designed with quick release and medical access features.
If the soldier gets into a very difficult spot, like underwater, then the individual can very quickly release the armor packs, and that gives them more mobility.
Mobile, light, and strong. A fully equipped modern vest can withstand a .30-06 Springfield M2 armor-piercing round at normal range. But body armor is designed for a very specific task. Disposing of bombs and the increasing use of IEDs calls for protection that is quite different from taking an impact from a bullet. Most people wearing bulletproof vests in combat will probably be shot at from some distance, with a projectile optimized in shape to penetrate materials, a known threat. This is not the case for individuals attempting to disarm an improvised explosive device, a landmine, or an unexploded warhead. Up close and personal, the soldier will potentially be exposed to fragments traveling at incredibly high velocity, possibly even 12,000 to 15,000 meters per second as they're accelerated by the explosion. But that threat can be countered by the advanced bomb suit.
With a bomb suit, you've got to deal with a much more intense threat. It's of paramount importance to use thick materials that are able to deal with the loading that you get from an explosive blast.
In the aftermath of the London Blitz, bomb disposal teams worked largely unprotected when neutralizing unexploded ordnance. In the decades since, suits have evolved to become sophisticated pieces of military equipment, designed to withstand extreme force, while allowing the wearer clear vision and mobility.
Bomb suit is generally made from multiple materials. So we would use high-strength steels or ceramics to deal with the fragments that you would get from an exploding munition or an exploding IED. And we use high-performance fibers such as Kevlar. And we use heat-resistant fibers as well, so fibers that are able to deal with the heat of an explosion.
All of these materials combined can offer protection from the shrapnel of the explosion. But it does little to defend against the shock of the blast.
So we use foam, and what the foam does, it mitigates the shock that you get from the explosive blast as it transmits from the bomb suit to the human body. And that increases the level of survivability for the occupant.
Every battle is an arm wrestle, an examination conducted by an attack on a defense. And the history of war is the story of the evolution and adaptation of offensive and defensive tactics and the machines used to fight them. The IED has changed the nature of warfare, and tactics and equipment have evolved to defend against it, just as they have in every aspect of warfare. And they will continue to do so. Over the course of military history, two elements have been locked in an ongoing struggle for battlefield dominance: firepower and maneuverability. True battlefield potency is achieved when you're able to take your firepower, your army, and maneuver it through a war zone to gain a positional advantage. But in the 70 years before the start of World War I, the technology of firepower had advanced at a much greater rate than maneuverability, which still plodded along at the speed of a horse. That would all begin to change during World War I, with the emergence of an array of new technologies, at the heart of which was the revolutionary internal combustion engine. And with these technologies came war machines designed to restore the balance, machines that matched the advances of weapons with an ability to move men faster, more efficiently, and more safely. This is the story of movement. disparity between mobility and firepower was no more starkly evident than during the Gallipoli landings of 1915. The first major amphibious operation of World War I followed a centuries-old tradition. And in the pre-dawn of April the 25th, a flotilla of wooden boats began quietly rowing men ashore from transport vessels anchored 500 meters away. But as they slowly came within range of the beach, all hell broke loose.
Essentially, each lifeboat could carry up to 28 diggers. And they were all compressed in there like sardines, and they were under enemy fire.
Heavy shelling and gunfire rained down, and the men in those wooden boats were helpless.
What was notable about the Gallipoli landings was the rate at which the troops could get on the ground and start fighting. They were limited by the fact that they had to climb over the side of the boat.
The days of amphibious operations led by rowboats were over. But soon, a new type of vessel for moving men ashore would emerge. While the Second World War provided the Allies with the same problems faced at Gallipoli, they were on a much grander scale. How to deploy entire armies and supplies to a continent where all the major ports were in the enemy's control. Enter the American boat-building entrepreneur Andrew Higgins and his design, the LCVP. Higgins answered the call of the U.S. Marines to construct a vessel that could perform well in the open sea and deliver a company of 36 fully equipped soldiers onto unprepared beaches. Based on a design used in the shallow waters of the Louisiana bayous, the initial landing craft personnel, or LCP, could operate effectively in just 45 centimeters of water, land its bow ashore, and remove itself to deeper water as needed. This initial design was adequate, but required men and supplies to be unloaded over the sides, a tactical nightmare considering the dangers of amphibious landings.
So they decided to use a deployable ramp which fell down, which allowed a rapid evacuation of the craft. And that meant that the troops could get straight onto the beach and start fighting as soon as possible.
What's more, they could be equipped with 2 Browning machine guns at the rear to provide covering fire while unloading. This design became known as the Landing Craft Vehicle Personnel, LCVP, or Higgins boat for short. With its ability to carry a full complement of 36 combat-ready infantry, it would play a vital role in the D-Day landings of 1944. Close to 2,000 Higgins boats were employed in those landings. So critical was the role they played that after the war, Supreme Allied Commander Dwight Eisenhower declared that Higgins is the man who won the war for us. But the Higgins boat was not the only amphibious landing craft that would play a vital role in the war. In virtually every theater of World War II, the Allies were compelled to launch amphibious operations. But arriving onto land from the sea presented the question of how to assist troops as they negotiated that most treacherous element of any beach landing, the open expanse of the beach itself.
Remember, landing craft can only get you onto the beach. To get from the beach into, say, cover, if you have to carry things, you're vulnerable. So in 1942, the Americans, of course, invented an amphibious truck. And this was the DUKW, known, of course, as the Duck.
The Duck exemplified one of the most remarkable traits of the American war effort: rapid manufacturing adaptability. Rather than create an all-new vehicle from scratch, they took the proven CCKW 2.5-ton truck, the logistical backbone of the Allied war effort, fitted a boat-like hull to the existing drive chain and chassis, and then added a rear propeller and bilge pumps, both powered through a transfer case.
So it could drive on the road as normal, and the good thing about it, it could swim.
The DUKW, of course, is inherently a ludicrous device. This is a truck that floats, you're kidding me. And the American Armed Forces initially rejected it. It just happened that an experimental model happened to be on the coast of Massachusetts when there was a hurricane in 1942, and there happened to be a Coast Guard patrol vessel that had got into difficulty, and the boats couldn't reach it, but the DUKW was able to literally swim out, pick up the crew, bring them back. And after that, all of the objections to the DUKW concept were disappeared.
And when it was introduced into service, it was a revelation.
Because it goes both on sand and mud and on coral and on roads, it needs wheels that can change their tire pressure. How do you do that? The Americans have this thing called a Spears device, common in cars today, which enables the driver of the DUKW to vary the tire pressure of his wheels. So in lots of ways, the DUKW confronted and solved a whole host of technical problems.
Over 20,000 ducks were produced, and they saw service in every campaign until war's end. Able to reach 80 kilometers per hour on land, and with a range of 650 kilometers, which allowed them to continue supply as the main front advanced. The Duck is often referred to as one of the machines that won the war.
The DUKW was immediately a massive success because at landings like Normandy, the Dragoon landings in the south of France, the further Italian landings right through the Italian campaign.
But where it really earned its stripes was in the war in the Pacific, fighting alongside another amphibious vehicle that would prove invaluable. Its more heavily armed and armored cousin, the landing vehicle tracked. Perhaps the most memorable of all land battles in the Pacific was the Battle of Iwo Jima. On February 19, 1945, the largest American naval force ever assembled in the Pacific began its attack on the small island, part of an inner ring of Japanese defenses designed to prevent an American invasion. Anticipating an amphibious war, the Americans understood that simple landing barges would not cross the coral reefs and sandbars that fringed most Pacific islands. And the boggy volcanic sand of the beaches often ruled out wheeled vehicles for the initial assault. Based on a tracked civilian vehicle designed to navigate the swampy terrains of the Florida Everglades, the LVT provided a solution.
The LVT was a landing craft that was fitted with tracks.
With tracks, you have 2 points of contact on the ground over a large area, so your ground pressure is a lot lower.
So whereas wheels would get stuck, tracks are still able to keep the vehicle moving forward.
With the capacity to transport 6 crew and 30 troops, the LVT was powered by a 7-cylinder, 186-kilowatt radial engine. The addition of a rear folding ramp meant that light vehicles and artillery systems could be carried, further enhancing the LVT's capability. With the rear ramp in place, troops and vehicles could exit with relative safety using the hull, which was covered in 13mm armor as a shield.
And that is so important with a landing craft. The reason being is that very often you're landing under duress. You're landing under conditions of enemy fire.
Initially a supply and transport vehicle, when experience pointed to the LVT's offensive potential, 2 30mm and 2 50mm guns were fitted forward and rear of the loading area. Updates continued with gun turrets and suspension lifted from the Stuart Light tank. It was another example of American manufacturing adaptability. Nearly 20,000 LVTs were produced, an all-new kind of infantry fighting vehicle that played a central role in the Battle of Iwo Jima, a costly battle that lasted a month before U.S. Marines claimed victory. The LVT-4, The variant used with such success during the month-long Battle of Iwo Jima continued in service after World War II and was superseded by the massive 40-ton LVTP-5. It in turn was replaced in the early 70s by the LVTP-7, a family of vehicles known by troops as the Amtrak or Battle Bus. And in 1984, a shift in capability and tactical use, leaning more toward all-round fighting capability, led to a name change. No longer principally a landing vehicle, the LVTP-7 became an amphibious assault vehicle and was redesignated the AAV.
The amphibious assault vehicle is a fairly substantial improvement on its historical predecessors, such as the LVT and the W. The revolutionary aspects of the design are based on three things. Firstly, it's protection. So it has an aluminium hull, but also it is able to be fitted with a ceramic-based applique armor.
Made from sandwich-plated steel, combined with an underlayer of Kevlar, the enhanced applique armor kit provides protection against small arms of up to 14.5 millimeters and anti-material shell fragments.
The second point is its speed.
With a weight of just 24 tons, the AAV, operated by a three-man crew, can transport 25 combat-loaded Marines on roads at speeds of 72 kilometers per hour. War doesn't wait for weather, and the pronounced bow of the fully battened-down AAV can withstand swells of up to 4 meters. And it can do this traveling at speeds of up to 8 knots, propelled by the vehicle's tracks, which are assisted by a pair of water jets fitted to the rear of the track idlers. All round, this represents almost a doubling of speed and seagoing ability than that achieved by the LVT-4.
The third aspect of this vehicle is its range, in that it's able to travel up to 480 kilometers on a single tank of fuel.
A range double that of the World War II LVT-4. The roofline features a turret equipped with an M2 50 caliber machine gun and an MK19 40mm automatic grenade launcher that can accurately strike targets at a range of 1.5 kilometers. AAVs have powered ashore in a variety of conflicts, including the First Gulf War. And while it has developed into a highly adaptable battlefield weapon, it is still very much an amphibious vehicle, capable on land, but not of the land. To reinforce an amphibious assault and continue that attack on land requires vehicles with both high levels of armor and heavy-duty firepower. And to deliver these vehicles from ship to shore requires a heavy-duty landing craft, like the LCAC.
The landing craft air cushion is a huge hovercraft, and it's awesome. It's able to carry up to 188 troops, over 60 tons of payloads. That means that it can take an M1 Abrams from ship to shore.
Launched from the floodable well deck of multi-purpose amphibious assault ships, the LCAC is powered by 4 12,000 kilowatt turbines, has a top speed of over 70 kilometers per hour, and a range of up to 550 kilometers.
The revolutionary thing about the LCAC is that it can be deployed from a ship up to over 50 kilometers away. So that means it can traverse from a point which is over the horizon from the destination. That means that your expensive assets, the large ships that deploy this craft, are protected from enemy fire.
The LCAC also has survivability built in. While the 4 main engines are all used for lift and propulsion, the craft can continue to operate at reduced capability with 2 engines inoperable.
The other advantage of the LCAC is it can be deployed almost anywhere. In fact, it's able to be deployed on around 80% of the world's coastlines.
Due to its tremendous capability over hazardous terrain, a small army can be deployed beyond the beach in secure landing areas, where they are less vulnerable to enemy counterattacks. And among that force would be a number of armored personnel carriers. Just as amphibious vehicles have had to evolve to meet the challenges of getting soldiers to the battlefield, land-based troop transport has had to adapt the way it moves them on it. At the turn of the 20th century, motor vehicles had yet to gain military acceptance, and aviation was in its infancy. Just as rowboats were the accepted method for amphibious landings, trains and horses were the traditional tools used to move men and equipment on land. But railways follow static routes, and horses are flesh and blood. And it was this lack of flexibility and speed that contributed to the stalemate that was World War I. A costly impasse that lasted for over 4 years. But as the reliability and power output of the internal combustion engine improved, new ways of transporting men began to emerge.
World War I was the first major conflict where vehicles were starting to be used. And the main advantage of a truck is that it's a little bit more resilient than a live animal.
In the Scientific American magazine of July 1916, an article appeared describing the French efforts to defend the citadel city of Verdun. As if surprised, it reported that it was here then that the motor transport performed its miracle of bringing up 250,000 men, supplying this great force with food and ammunition, and removing the wounded. It went on to say that it was the first time in the history of the world that any army was entirely dependent on motor transportation. The narrow road to Verdun was later renamed the Sacred Way to commemorate its vital contribution to the war effort. But while trucks and buses became increasingly used in World War I to move men to and from the battle zone, movement on the battlefield itself remained relatively static.
And of course, at that time, breakdowns in trucks were quite commonplace.
It wasn't until World War II that the geographic scale of warfare meant that the mass movement of men across the battlefield by motorized vehicles would no longer be a fallback plan, but a necessity. It was the German Blitzkrieg of 1939 and 1940 that first clearly demonstrated the tactical advantages of coordinated, motorized battlefield transport.
Blitzkrieg is a term basically for lightning war. So you want to hit one spot very quickly and fast. So you essentially just break through.
To achieve success, Blitzkrieg relied on specialized vehicles to transport troops and supplies. Specialized vehicles known as Hanomags, a family of half-track troop transports. Perhaps the most famous and widely used of those German machines was the ST KFZ 251. A robust and reliable half-track that weighed 9 tons, had a top speed of 55 kilometers per hour, and a range of over 300 kilometers.
It had the maneuverability of a wheeled vehicle, but still had the load-carrying capacity of a tracked vehicle over soft and boggy ground.
By combining track drive with steering wheels, the Hanomag was able to ford close to 1 meter of water and cope with all but the most treacherous terrain.
The German half-track was a troop carrier, so it principally was designed specifically to get 10 troops to the front, to the action, to where the battle was, under the protection of steel armor.
Operated by a 2-man crew, the Hanomag was armored with 14.5 millimeter thick front-facing steel plates that were steeply angled, and V-shaped plates of 8mm thickness on the sides, providing more than adequate protection against small arms and machine gun fire.
What's interesting about the half-track is the armor plating that's used. And if you look at a half-track, it has these angled plates. Now, there is benefit there from a ballistic protection point of view, because as the bullet travels through an oblique plate, it has the tendency to turn, and what that does is that takes energy out of the bullet.
The Hanomags were central to the success of the Blitzkrieg, and at least 15,000 were produced in a number of variants during the course of the war. The Allies, too, used half-tracks, and perhaps the best known of those was the American M3, which was almost identical to the Hanomag in both specification and production numbers. The M3 would go on to serve with the U.S. Army through both Korea and Vietnam. But the speed and weapons of warfare eventually outpaced vehicles like the Hanomag and the M3. And a new generation of faster, more heavily armored land transport emerged in the early 80s with the M2 Bradley. The U.S. Marine Corps described their fighting philosophy as seeking to shatter the enemy's cohesion through a variety of rapid, focused, and unexpected actions. That philosophy, put more simply, reads, move men and armor quickly. Powered by an 8-cylinder diesel engine and operated by a crew of 3, the M2 Bradley can carry a squad of 7 combat-ready infantry at a maximum road speed of 65 kilometers per hour across an operational range of 450 kilometers. This fulfills one of the main design objectives of the M2 Bradley, which was to keep pace with the Abrams battle tank, with which it often fights in formation. However, speed in battle is not the only consideration for armored personnel carriers.
Whenever you're transporting troops from one location to the next, then you need to get there as quickly as possible. The less time you spend on the road, the less likelihood there is of being hit.
Of course, speed is worthless without maneuverability. And the M2 rides on a torsion bar suspension system with a track that sits on 6 double-tired road wheels, giving the 36-ton vehicle exceptional all-terrain capability. And that mobility is matched by protection.
If you look at something like an RPG-7, which has an 89mm diameter cone, that can penetrate up to about 300mm of rolled homogeneous armor steel. So it's a very deadly threat indeed. And of course, most armored vehicles, such as tanks, they don't have 300mm of steel on their hulls to provide the level of protection that they require. And so you need another means of providing protection.
To combat this, the M2 has been upgraded with additional applique steel armor and the latest explosive reactive armor, which consists of 96 tiles fixed to the sides, turret, and front of the vehicle, which effectively enhance protection against a variety of anti-armor munitions, like the RPG-7. While their main mission is to provide protected transport to a squad of troops to and from critical points on the battlefield, the M2 can provide supporting fire with an array of cannons, machine guns, and even the TOW anti-tank guided missile system. The M2 Bradley has experienced continued success since its introduction in 1981. Yet the Bradley was developed at the height of the Cold War, around the expectation that if a war were to take place, it would likely be a high-intensity conflict in Europe, fought along traditional lines. However, recent conflicts in the Middle East and elsewhere have proved to be, in many ways, anything but traditional. The changing conditions have demanded a fast, adaptable vehicle to meet new battlefield challenges. And that vehicle is the 8-wheeled IAV Striker.
Protected mobility vehicle. And the idea is that it's there to transport troops very quickly from one location to the other.
Providing armored protection for a 2-man crew and a squad of 9 infantry soldiers. Everything about the Striker is designed for speed, adaptability, and survivability. Its 8 wheels can be switched on the fly between 4-wheel drive on made roads to 8x8 configuration for rough terrain, where it can achieve speeds of up to 100 kilometers per hour. But the 8-wheel design is more than just a novelty. It follows a modern trend based on battlefield experience.
One of the interesting design features of the Striker is that it has multiple wheels. It has 8 wheels. So that means once it goes over a mine, and if that mine goes off and you lose a wheel station, it doesn't kill your mobility. And that can be essential if you're trying to get out of a very hot spot on the battlefield. Tracks, on the other hand, if you run over a mine and you destroy your track, then that means that you've lost your mobility and effectively you're a sitting duck.
Less an armored fighting vehicle like the Bradley and more a counterinsurgency weapon, being wheeled, the Striker is far quieter on approach, giving the troops far greater opportunity of overwhelming their objective by stealth. Of course, protection is paramount for a vehicle designed to deliver troops to the heart of battle. And while the Striker is heavily armored, combat experience in Iraq pointed towards the need for countermeasures against the anti-tank weapons it encountered. And so the Striker was retrofitted with a cage of slat armor. But perhaps the greatest advantage of the Striker, compared to the Bradley, is its weight.
The back end of the Cold War, the US Army was specifically looking for a vehicle that they could deploy very quickly around the world. And mass is a very big consideration when you're looking at deployability. That is, that you want to reduce the weight of your vehicle as much as possible, but still maintain features like good levels of protection, perhaps in some cases, good levels of lethality. And the IAV Striker is one vehicle that had the possibility of offering those.
While the Striker is lethal, with a universal mount that can accept the remote weapon station, a modular unit which can fit a variety of weapons as needed, from heavy machine guns right up to a 105mm rifle cannon, it weighs a comparatively light 17 tons. As such, it forms the basis of new, highly mobile units referred to as brigade combat teams. Each brigade operates more than 300 Strikers of different variants. And that lighter weight contributes to the ability for an entire brigade to be airlifted and deployed anywhere in the world within 96 hours. And that speed of deployment can only happen one way: by air. While the aircraft of 1918 were extremely primitive, their obvious fighting potential saw most of the military functions of modern aircraft in place by the end of World War I, with just 2 notable exceptions: the cargo aircraft and the helicopter. The interwar years saw rapid developments in the range and carrying capacity of civil aircraft. And during World War II, the potential of transport aircraft was unlocked, and militaries began moving men and equipment in ways that no one had ever imagined. In December 1935, an aircraft was introduced into domestic service in the United States that many have referred to as the most important aircraft ever built: the Douglas DC-3. The smooth, round, aerodynamic shape, which minimized the drag effects of greater size, were revolutionary at the time. Combined with powerful engines and retractable undercarriage, the all-new shape gave the DC-3 a top speed of over 300 kilometers per hour, which was extraordinary for its day. As was the wing design, enabling the DC-3 to take off and land from short, unprepared airstrips. It wasn't long before its military potential was realized, and in 1939, the C-47 Skytrain was born. Differing little in appearance from its domestic cousin, slightly more powerful engines increased the C-47's top speed by 30 kilometers to 360 kilometers per hour, and left it with a usable range of 2,750 kilometers.
This aircraft was used both for troop transport and cargo. And so in many campaigns in Europe, in the Pacific, these aircraft were the prime airlift asset, really, for the Allies.
With the ability to haul 28 combat-equipped troops and to land and take off from rough fields less than 800 meters long, the C-47 could quickly deliver men and material close to the front lines. Designed for loads of up to 2,750 kilograms internally, food, medicines, ammunition, and machine parts for mechanical repairs could all suddenly be moved to the front lines by air. But perhaps the most revolutionary role undertaken by the C-47 was in airborne assault operations. Where there was no place to land, but supplies and men were needed, the C-47, with its remarkable low-speed control, was ideal for delivering them by parachute.
Really, it was the Second World War that saw the huge advent of paratrooper operations. In fact, we looked at campaigns like D-Day, where very large numbers of troops were delivered out the back of fixed-wing aircraft, like the military version of the DC-3, or in fact from gliders being towed behind these aircraft.
In all, over 10,000 C-47s in different variants saw service during World War II, deploying thousands of troops and supplies into critical combat areas. In this role, it was central to the establishment of the modern concept of airborne warfare, restoring a balance to the wartime firepower maneuverability equation. A balance that would be tipped further in favor of maneuverability with the introduction of the helicopter. Helicopters saw limited service in World War II, but the fragile design of the first truly functional helicopter, the German Focke-Wulf FW-61, spawned a number of aircraft, both German and Allied.
To that point, helicopters had existed and were used operationally, but had been piston engine powered. Those sorts of engines, of course, had been the predominantly used engines in all aircraft, really up until the end of the Second World War.
On land, personnel carriers had become the modern equivalent of the cavalry. But during the Vietnam War, the conditions worked against land-based transport. They were relatively slow-moving in the jungle terrain and easily engaged by a hidden enemy. The solution was to get the cavalry airborne in numbers that would make a difference. To achieve that required a breakthrough in engine technology. And that breakthrough came with the development of the turboshaft engine.
This French helicopter, known as Alouette II, is the first whirlybird to be fitted with a gas turbine. Up till now, speed has never been a strong point of the helicopter, but with 360 horsepower to help it along, it's quite a different story.
Whereas the engines in fixed-wing aircraft were predominantly something called a turbojet, which was utilizing the exhaust thrust of the engine. The variant of the gas turbine used in helicopters was actually known as, or is known as, a turboshaft. And gas turbines actually were developed to give much better power-to-weight ratios and reliability than piston engines.
It was that dramatic change in power-to-weight output that allowed for the design of an aircraft to fill the air cavalry role. And the Americans turned to a helicopter designated the Bell UH-1, codenamed the Iroquois, but affectionately known as the Huey. The sight of Huey's landing with armed troops spilling from either side is one of the defining images of the Vietnam War. Designed from the outset to move men, its large cabin space was sufficient for 14 combat-ready troops, who gained access through large, sliding, windowed doors on either side of the fuselage. With a base crew comprised of 1 to 4 personnel, depending on the task and equipment utilized, the Huey, powered by its turboshaft engine, could vertically lift a payload of 1,750 kilograms and then move it at a top speed of 220 kilometers per hour. And like the ground and water-based machines that evolved from simple troop carriers to offensive weapons, so too did the Huey.
So gradually they became more and more armed as helicopter gunships. So with forward-firing machine guns and rockets, and also with door guns that could be fired by troops on board in support of those on the ground.
Hueys in Vietnam were called upon to fulfill a variety of roles that few aircraft of the time could match. But perhaps their greatest achievement was in medevac operations. With 6 medical litters filling the cargo space, Hueys were responsible for airlifting an estimated 90,000 injured troops through the course of the Vietnam War. While the Huey could move men quickly, battle often calls for heavy weapons to support troops. And to move heavy equipment is the task of a heavyweight, like the Boeing CH-47 Chinook.
The Chinook is a heavy lift helicopter. It was designed to be both a cargo carrying and troop carrying helicopter that first saw widespread service in the Vietnam War.
Despite being introduced in 1962, the Chinook is still one of the heaviest lifting helicopters in the world and one of the fastest in the U.S. military inventory. A durable twin-engine tandem rotor helicopter, the Chinook was originally designed as a troop transport and supply vehicle, and as such is capable of carrying as many as 55 combat troops or 24 medical litters. In fact, in Vietnam, the Chinook transported over 670,000 passengers in its first 2 years of service alone.
But it quickly very much saw favor actually carrying equipment, particularly things like artillery.
Powered by twin turboshaft engines that have been constantly upgraded since its introduction, the Chinook can lift nearly 12 tons using 2 counter-rotating rotors that eliminate the power drain of the anti-torque tail rotor found on single-bladed helicopters.
The helicopter generates lift, not by forward motion, but by the rotation of its main rotor. And so the Chinook was able to basically double the surface area of rotors by adding a second rotor disc and simultaneously achieving the torque balance so that it could cope with different distributions of mass in the vehicle.
This makes the Chinook incredibly stable while hovering over a specific location. And so, where the Chinook really excels is in the deployment of artillery, gun crews, and transport vehicles to inaccessible locations in support of frontline troops. Using a triple hook system which provides in-fight stability, large external loads such as 155mm howitzers or armored vehicles can be transported to the front line at speeds of up to 260 kilometers per hour. For half a century, the Chinook has been central to maintaining the maneuverability of troops and equipment so essential to modern warfare. And when it started life, it shared that job of moving men with the Huey. And it continues to offer that same support to the Huey's replacement, the Black Hawk. Helicopters like the Huey and the Chinook ushered in a radically different way of fighting war. But all new methods of attack are eventually countered by adaptations in defense. And with time, the Huey became increasingly vulnerable.
While helicopters had the utility of being able to operate very close to the fight and in close support of that fight, of course, that made them targets, made them susceptible to things like shoulder-launched infrared missiles.
Enter the Black Hawk, the most widely used military transport helicopter in the world today.
The Black Hawk very much took over the role of a battlefield utility or battlefield transport from the Huey.
The Black Hawk addresses the Huey's perceived shortcomings in every respect. The first being power.
The Black Hawk is a larger, heavier, higher performance helicopter, and so it uses two engines to drive its main rotor.
Twin engines increase survivability, and with a top speed of 294 kilometers per hour and superior ballistic protection, it is far less susceptible to small arms fire. The Black Hawk incorporates a number of other design features that add flexibility to that survivability. With the capacity to carry 11 troops with equipment, it can also lift 1,200 kilograms of cargo internally, or 4,100 kilograms externally by sling, which equates to a 105mm howitzer, along with 30 rounds of ammunition and a 4-man crew in a single lift.
The Black Hawk has found application in a number of different roles.
With an armament that can include anything from machine guns to Hellfire missiles, the Black Hawk is equally accomplished in both defense and offense. In addition, it is equipped with enhanced stealth capabilities.
Any gas turbine will have a very hot exhaust plume, and that is a perfect target, both in terms of surveillance, but then also for shooting down that aircraft. And so the Black Hawk uses an infrared suppression system to try and hide and cool the hot exhaust of the engine before it is completely exhausted.
While helicopters like the Black Hawk have changed the way we fight, they still suffer from relatively slow speed, short range, and limited lifting capabilities, leading aircraft designers to search for ways to combine the attributes of both helicopters and conventional airplanes.
A helicopter will always suffer compared to a fixed-wing aircraft because it doesn't have the benefit of that forward motion to develop lift over wings. Current and future designs are looking for, can we do this better? And we are now seeing the advent of hybrid designs like the V-22 Osprey that can actually transition almost from a traditional rotating rotor blade generating lift to forward speed with pusher propellers and small winglets.
But until a truly viable solution emerges, the serious heavy lifting on the front lines will continue to be shared by helicopters and an aircraft that is the longest serving in U.S. military history, the C-130 Hercules.
The C-130 Hercules is a 4-engined, turboprop-powered transport aircraft.
Perhaps the best-known military transport aircraft in the world, the Hercules is an aircraft that continues to evolve to match the changing demands of modern warfare. First introduced in 1956, the latest variant of the Hercules, the MC-130J Commando II, meets the needs of a modern mobile attack force with the ability to refuel an array of modern helicopters in flight and support special forces in forward operations, either by air drop or air land. It is the most recent in a series of role shifts and upgrades to a machine that began life as a simple transport aircraft, one that has retained its classic shape, a silhouette familiar to generations.
The C-130 sits sort of in the middle of the tactical and strategic role. So it's not as big as its compatriots like the very large C-5 Galaxy or the C-17 Globemaster. So it is not optimized for intercontinental transport. It is designed, though, to be able to go into what we would call tactical airlift, where it can take payloads into unmade runways in forward operating zones.
The story of the Hercules began in 1951, with America committed to a war in Korea and an emerging requirement for a different kind of aircraft. Lockheed responded with a machine that combined the required lift capacity with low-altitude, low-speed flight control in a design that has proved incredibly adaptable. Entering service just 11 years after World War II, what the C-130 demonstrates is the incredible speed with which aircraft developed. With the capacity to carry in excess of 20,000 kilograms, the C-130 has 7 times the lift capacity of the C-47. What it provides is a platform that can deliver a sizable, fully equipped, and mobile fighting force into a war zone at a speed in excess of 600 kilometers per hour. A speed and capacity that just 10 years previous would have been unimaginable. And while never optimized for intercontinental transport, the C-130 has a range of over 4,000 kilometers, allowing for medium-range tactical operations that double the distance covered by aircraft like the C-47. And just as landing craft and personnel carriers have evolved from simple transports to take on important strike roles, the C-130 is one part of an ongoing quest for increased battlefield mobility. All modern militaries are mindful of the great human cost of war. And while we continue to have conflicts, social attitudes, combined with the reach of modern media, has created a new accountability around them. Mass deaths like those seen on the battlefields of World War I, or indiscriminate bombing like that seen in World War II, are unacceptable in the modern age. Increasingly, the technological advances of the machinery of war have resulted in a growing reliance on machines that, rather than moving men and equipment to and across the battlefield, are instead removing them from the battlefield altogether. Unmanned and autonomous machines may seem like the stuff of science fiction, but they have been slowly transforming the nature of warfare for decades. And it seems likely that the battlefields of the future will be dominated not by men, but by machines. Speed has always been one of the greatest weapons of war. To take advantage of the enemy's unpreparedness, to travel by unexpected routes, and strike quickly where it is least expected, is a key to battlefield success. And throughout the 20th century and into the 21st, the speed with which technology has altered the machinery of war has been electrifying. From bolt-action rifles to machine guns that can deliver over 500 rounds per minute, the first jet fighters to long-range ballistic missiles, and the humble Jeep to the most advanced high-speed troop carriers, the capacity to shoot, move men, and strike with speed and flexibility is synonymous with modern warfare. This is the story of agility. Since they first appeared over the battlefield, the sheer wonder of flight has made aircraft perhaps the most glamorous of all the machinery of war. Machines that have continuously pushed the boundaries of technology in the quest for speed and agility. Modern fighter aircraft are designed to respond to threats quickly and effectively in situations where mere minutes can determine outcomes. They are the pinnacle of a quest for agility that began in World War I, a quest that appeared to have stalled during World War II, but one that gained new life in the dying days of the war with the introduction of a new power source, the jet engine. Introduced in 1944, the first jet-powered combat aircraft to enter service, the Gloucester Meteor, very nearly didn't get off the ground. The heat generated by the new turbojet engines were deemed beyond the bounds of metallurgical science of the period. But it did, and those engines, designed by Englishman Sir Frank Whittle, opened a new world of possibilities for aviation.
The turbojet engine was a dramatic change in design philosophy. The conventional piston engine was incredibly complex. We ended up with radial engines that were multi-rowed, even up to 4 rows. Heating was a problem. And then Frank Whittle designed this thing called the jet, which was so simple because it was all rotating basically on one shaft. They had a compressor at the front of the engine. It was, in its early days, incredibly simple.
The advantages of jet propulsion were many. More power was the most obvious, which allowed greater payloads. And in wartime, that translated to greater all-round attacking and defensive capability. While the combustion efficiency of jet engines gave them the ability to operate effectively at higher altitudes, importantly, jet power meant the Meteor could also maintain top speed at lower altitudes, something which piston-driven aircraft could not, which gave it the speed to catch the low-level V-1 flying bomb. The Meteor was in every way a record breaker. With a top speed of 960 kilometers per hour when it entered service, it was faster than anything that preceded it. And its excellent rate of climb of over 760 meters per minute made it possible to reach its service ceiling of 10,000 meters in as little as 12 minutes. While the Meteor design was not without issue, it served a greater purpose in advancing a technological cause. A cause the Harrier jump jet would take to another level. Speed is one aspect of agility in the air. Flexibility of purpose is another. As fighter aircraft increased their airborne capabilities, they also required increasingly large infrastructure to support their operations. To overcome these service limitations, the British came up with the Harrier, the only true vertical short takeoff and landing aircraft created during the Cold War. And with it came a new dimension in airborne agility.
It was an aircraft that was developed to remove reliance on runways. And so it could be operated right at the front of the combat arena.
What allows the Harrier to provide that frontline support directly from improvised bases, such as car parks and small flight decks, is a rather unique high bypass turbofan engine working with an ingenious engine vectoring system. 4 exhaust nozzles, 2 operating off the fan at the front of the engine and 2 off the exhaust at the rear, are used to direct a proportion of the overall thrust.
And it could swivel these exhaust nozzles from pointing backwards, which you would normally do on an aircraft, down to vertical, so that it could take off vertically if needed. It could land vertically, and even it could swivel them slightly forwards, thus moving the thrust vector and allowing it to maneuver quite differently than a normal aircraft.
This ability to vector thrust makes the Harrier capable of incredible maneuverability at speed in normal operations. Continuously revised and updated since it was introduced into operational service in 1969, the current Harrier II is an evolution of the original that has transformed the aircraft into a more versatile combat platform. No longer tied to basic close support sorties as its only forte, modern systems have given the Harrier combat capabilities that make it a premier ground strike aircraft with unparalleled attack helicopter-like agility that no conventional aircraft can match. But one thing it doesn't have is raw speed. Something the MiG-29 has in spades. As with so many weapons developed during the Cold War, the MiG-29 was designed to be the #1 air superiority fighter in the world. In this case, it meant it had to be faster and more maneuverable than the lightweight F-16, an aircraft with an impressive thrust-to-weight ratio that could perform radical maneuvers with surprisingly little energy loss. First flown in October 1977, the MiG-29 matched its competitor in almost every performance measurement. Both have top speeds of 2,400 kilometers per hour. Both have a thrust-to-weight ratio of 1.09. But where they differ is in wing area. The MiG has 30% greater, and that makes it significantly more stable and maneuverable at lower speeds. Utilizing this super maneuverability, the MiG-29 can perform the highly complex Pugachev's Cobra, an aerial feat which would cause a conventional aircraft to stall and lose altitude rapidly. And while both can maintain sustained vertical flight, the MiG can achieve it surprisingly quickly after takeoff. And its capacity to maintain a very high angle of attack means that it climbs at an astonishing 330 meters per second, significantly quicker than the F-16. But as technology continued to alter the tactics on the battlefield, neither the F-16 nor the MiG-29 were ever truly tested as fighters in the way they were designed. Despite the end of the Cold War, both militaries continued to push the boundaries of aeronautical engineering. And when the Americans took the means of propulsion first used in the Meteor, added the aerodynamic agility and the speed of the MiG-29, the operational flexibility of the Harrier, and then installed the latest weapons and electronic systems, they created an aircraft that is beyond compare. The F-35B Lightning II. The basic concepts behind the F-35B were actually developed by Lockheed Martin's Skunk Works as a potential replacement for the Harrier over a decade ago. That idea was originally shelved, but it resurfaced as part of the Joint Strike Fighter program,
which then evolved into the F-35A, B, and C. This was a design that was promised to be able to replace not just the Harrier, but a whole range of aircraft on a range of missions, both in the marine role of STOVL, of short takeoff and vertical landing, but also in the more traditional fighter and ground attack role for the US Air Force.
What has emerged is an aircraft that has all the attributes of a frontline strike fighter, but with the capacity for STOVL.
One of the three variants of the F-35, the F-35B, is a short takeoff and vertical landing aircraft, which can take off without the need for a dedicated large runway, but then you can have all the attributes of a fixed-wing aircraft in terms of speed and range during most of your flight. But then when you want to come back and land, then you can land vertically, again, without the need perhaps for that dedicated runway.
Which it does in a stealth package with a top speed in excess of twice the speed of sound.
The F-35B uses some of the ideas from the Harrier, but takes quite a different approach in terms of the propulsion system.
Unlike the Harrier, the F-35B incorporates a separate lift fan system, powered via a drive shaft from the front of the engine, which works in conjunction with the aft thruster. Operating in tandem, they can direct up to 80,000 newtons of thrust from the engine to the vertical in just 2.5 seconds. The F-35B also has the most complex electronic sensor package ever fitted to a fighter aircraft,
which allows the pilot, via the very sophisticated head-up system in the helmet, to basically look anywhere they like around the aircraft, through the walls of the aircraft, and see what is going on in various wavelengths, in the visible wavelength, but also in the infrared.
All of the sensor data is collected and passed via the latest generation communication systems to other assets in the field, optimizing the aircraft as a part of a bigger system, hugely increasing its effectiveness and ultimately the capacity to effectively prosecute that conflict. The sum of over 60 years of technological advancement in aviation, it is an example of the constant growth in the performance requirements of the machinery of war, brought about by new technologies and battlefield innovation. Innovation that hasn't just affected fighter aircraft design, but also the design of their larger cousins. To attack from long range and to limit your opponent's capacity for agility is crucial in modern warfare. For many years, heavy bombers were the most effective way to damage infrastructure and supply lines, to soften targets, and to give attacking forces the best chance of exploiting their offensive capabilities. But World War II saw rapid improvements in the performance of fighter aircraft and ground-based air defenses. So much so that by the middle of the war, the old adage that the bomber would always get through was being well and truly tested. Even the most heavily armed bomber squadrons began suffering crippling losses. But in the immediate post-war years, the jet engine, more powerful and crucially able to operate at higher altitudes, not only saved the bomber's reputation, but made it all the more deadly. First flown in 1949, the Canberra was the world's first jet-powered strategic bomber, and its advanced design completely changed the rules for long-range strategic air warfare.
It was built by a company called English Electric, or only a very small company. They came up with the design, which was a revolutionary design at that time.
It bears some resemblance to the Gloucester Meteor, but unlike the first jet fighter, it was built without any defensive armament and simply relied on its top speed, which was in excess of 960 kilometers per hour, to outrun fighters.
There was need for an aircraft that could fly at fairly low level and at high level. We knew there were going to be ground-to-air missiles coming about, and so the greatest defence was altitude.
The Canberra's clean aerodynamic design could approach altitudes of 21,000 meters, well beyond the range of ground-based deterrents. But it wasn't aerodynamics that gave it the edge. It was an all-new axial flow jet engine.
The Avon engine in the Canberra was a pure jet, and it just had one shaft, and all the compressor blades, 12 stages, they were all on that one shaft. And so you got lots of thrust out the back, and it kept the compressor working.
Produced by Rolls-Royce, the Avon engine was a turbojet based on the earlier designs of Sir Frank Whittle, but one that produced significantly more power than anything before it.
They were very good for high altitude work, and they became quite efficient with fuel. The wings were designed to carry fuel as well as bladders in the fuselage.
Those bladders gave the Canberra a range in excess of 5,500 kilometers. All in all, it was 3 times as quick, could fly 3 times as high, and go 30% further than the Avro Lancaster, the ubiquitous bomber of World War II that preceded it, carrying an only marginally lighter 4,500 kilogram payload.
So the Canberra could take off with a full bomb load, quite a lot of fuel, go in low, and if they couldn't deliver the weapons on the first pass, go to another target. And so the Canberra was a very successful aeroplane with the armament load that it had.
So well was the Canberra designed for its purpose that there was no need to replace it, and had remained active with the British, US, and Australian Air Forces for over 50 years. Whereas one of the aircraft that took over its role in the late 1950s, one of Britain's famous 3 V-bombers, flew only once in anger, almost 30 years after it was first commissioned. The Avro Vulcan. The British had always valued strategic bombers, but as the Cold War progressed and advances in surface-to-air missiles made Soviet airspace virtually impregnable, the requirements of a strategic bomber dramatically changed.
When the Cold War started to get really, really cold, the Americans put the heavies on the Brits and said, look, you've got to do your bit.
And what was needed to do that was something that could attack from outside hostile airspace.
The Vulcan, the one I flew on, carried a nuclear missile as opposed to a bomb.
That weapon was a missile called Blue Steel.
The Blue Steel missile could get an incredible range of 100 miles. You dropped it 100 miles away from the target.
Blue Steel was not a small weapon. Rocket science was in its infancy, and in order to deliver its 1.1 megaton warhead, it was over 10 meters in length and weighed over 7,700 kilograms, almost double the Canberra's payload. And to get within range to fire Blue Steel, the aircraft that delivered it would have to penetrate enemy lines at either great height or extreme low levels, and at high speed to avoid interception.
The Vulcan itself was a delta shape.
The delta wing design of an aircraft adds the capability of super high speed. The swept leading edges are more aerodynamic and allow the wing to go through the air a lot faster.
The delta wing housed the 4 engines, initially Rolls-Royce Avons that it shared with the Canberra. And as advances in engine technology progressed, the Vulcan was repeatedly upgraded. The original Avon engines produced nearly 30,000 newtons of thrust. In its final incarnation, its 4 engines each produced over 60,000 newtons of thrust, giving the Vulcan incredible all-round agility. Able to carry a payload of over 18,000 kilograms, retirement of the Vulcan was underway at the outbreak of the Falklands War in 1982. By that stage, it had been retrofitted with in-flight refueling capability, giving it theoretically unlimited range. Several aircraft were dispatched from Ascension Island to attack the Argentinians in the Falklands. A round trip of over 12,000 kilometers, or 16 hours. One that stood for many years as the longest operation ever undertaken by military aircraft. While speed and agility is vital to prevent interception in the air, on the ground, it is the key to reinforcing an offensive advantage. And in World War I, the race to create faster firing, lighter, and more easily handled personal weapons began with the design of an efficient bolt-action rifle, the short-magazine Lee Enfield. In 1914, during the Battle of Mons in southern Belgium, a relatively small British expeditionary force, armed with Lee Enfields, fired on the German First Army.
It was assumed by them that the British were heavily armed with machine guns because of the rate of fire which was coming their way from the highly trained British Expeditionary Force.
Those British soldiers at Mons had been trained in a new way. And part of that more intense training included an annual test known as the Mad Minute. To pass, 15 shots had to be fired at a target almost 300 meters away within a minute.
Which is, out of a bolt-action rifle which only holds 10 rounds, is phenomenal. Gives you an idea of the skill set required to make that happen.
To achieve accuracy with a high rate of fire, combined with mobility, required an efficient, manageable rifle. And so everything about the Smelly, as it became referred to, was designed to optimize speed and agility. It was a rifle of carbine length, and at just 1 meter, it was easy to handle. It was comparatively light at 4.5 kilograms, and had a 10-shot magazine, which was larger than its competitors. What set the SMLE apart, though, was its rear-locking bolt, which meant far less travel and far quicker reloading. Over 5 million Lee Enfields were produced and saw service for much of the 20th century. But in the interwar years, the British, in pursuit of greater mobility, decided to create a weapon that had the brute strength of a heavy machine gun that could be operated by a single man. The Bren gun.
The Bren gun was a light machine gun that was introduced into British Army service in the mid-1930s.
And it's called the Bren because it was developed in Brno, which was in Czechoslovakia, now Slovakia, and it was built in Enfield, so B-R-E-N. And it became the most common British Commonwealth weapon of the entire war, and indeed of the world.
The first thing to note about the Bren is its weight, which at 11.5 kilograms is light for a gun of its power. What that meant was that while generally fired from the prone position, the Bren could also be fired from the shoulder with an accuracy comparable to that of a bolt-action rifle. A Bren gunner could also use his weapon on the move, firing from the hip, supported by a sling much like an automatic rifle, creating heavy suppressing fire during a forward assault.
It had a high rate of fire. It was 500 rounds a minute, but it only had a 30-round magazine, so it fired typically in short bursts, so it was quite economical to use.
And because the magazine was on the top, it could be quickly changed on the move.
So every man in a squad would be carrying a number of spare magazines to keep this hungry beast fed.
It was often used by a two-man team, one to fire, the other to reload and act as a spotter.
Each section of the British Army, and indeed Commonwealth armies, the Canadians, the Australians and New Zealanders, all structured their infantry sections around the gun group of these two men who would provide the organic fire support for the other 6 or 8 men in the section to do their job.
That second man was also responsible for handling an operation that kept the barrel cool and made the design of the Bren revolutionary.
By flipping a catch and by using the carrying handle, you could very quickly change the barrel in action, which meant that there would be no delay. You didn't have to wait for it to cool down. So the Bren's robustness was one of its best features.
The Bren's adaptability and portability meant that it could be distributed widely across infantry battalions. By the middle of World War II, the British were producing 1,000 Brens per week, allowing them to equip every infantry section, a group of 8 to 10 men in every single battalion, with its own light machine gun.
So in a sense, the Bren is at the heart of the tactics the British Commonwealth used to win the war.
But as World War II progressed, tactics and understanding of battlefield realities changed.
The assault rifle, as we understand it today, really emerges in World War II. Certainly the name assault rifle comes from the German Sturmgewehr, storm rifle, assault rifle, for that assault phase of an attack, or for trench fighting, or for urban combat. But the Kalashnikov, or the AK, as it's more commonly known, arguably perfects it.
The AK-47 was not the first assault rifle, but it embodied the best attributes of various earlier designs to create a weapon of extreme agility. Its gas-operated self-loading system was pioneered by the German Storm rifle. Its trigger mechanism is from the US M1 Garand, and its safety mechanism is a direct copy of that used on the Remington Model 8. But the Kalashnikov embraced other factors in its design to create the most agile and long-lived of all assault rifles. The first factor was climate. The AK-47 is made to operate efficiently in the same extreme conditions encountered during the war on the Russian front, where the dusty steppes of summer became frozen wastelands in winter. The second was reliability.
The way the Russian state has manufactured equipment, it's always been extraordinarily robust, which means it can take an awful lot of abuse and still work.
What's interesting about the AK-47 is that a child can maintain it. You can drop it into a swamp, pick it out, and you can very easily disassemble it and clean it up. It's got relatively few components compared to certain assault rifles. And so that is why it was so extensively used.
The third is flexibility. Kalashnikov can act as a semi-automatic or full automatic, depending on the battlefield circumstances, simply by moving a switch and pulling the trigger. It was and continues to be a rapid-firing people's weapon, designed for ease of use, one that can be quickly mastered by peasants and trained soldiers alike. And as such, it became the most highly produced and widely used personal infantry weapon of the 20th century. The introduction of powered vehicles revolutionized warfare. Machines like the tank, a self-propelling artillery piece with all-terrain capability, was one of the many technical advancements of World War I that meant World War II would be faster and far more mobile than any war that had preceded it. By taking the driveline principles of the tank, fitting it with a lightly armored skin and a powerful V8 engine, then arming it with a heavy caliber machine gun, the British created one of the most ubiquitous weapons of the war, the universal carrier. An extraordinarily agile battlefield workhorse.
The universal carrier is a very lightly armored tracked vehicle. It comes out of the fact that through the 1920s and 30s, European armies had fallen in love with the tank and were developing tanks to fight the next war.
The universal carrier was in essence an armored tractor. And as if to prove its universality, steering was through a wheel as opposed to the levers found in other tracked vehicles, which meant virtually anyone could drive it with limited training.
It's called universal because it can do lots of things. It can transport men, it can transport supplies, it can tow guns, and it was used all over the world to do that.
Powered by a Ford V8 engine, across the battlefield in any conditions, it was both agile and, for its time, quick, with a top speed of 56 kilometers per hour.
Tracked vehicles are able to traverse terrain which is extremely boggy and is able to get to they're able to get to locations that wheeled vehicles simply cannot get to.
The body was a simple steel box with a motor compartment situated in the center. In front sat a driver, and alongside him a gunner, usually operating the famous Bren light machine gun, which turned it into a highly mobile light attack vehicle.
And as the war went on, it was equipped with flamethrowers and mortars and all sorts of things to enable it to transport and fight on the battlefield.
With over 100,000 produced, it may have been one of the most ubiquitous, versatile, and agile weapons platforms of World War II. But when we turn our minds to the vehicles that defined World War II, it's not one of British manufacture that we think of. It's American. Any mental picture of World War II would be incomplete without the presence of at least one Willie MB, the vehicle better known as the Jeep. U.S. General George C. Marshall called it America's greatest contribution to modern warfare. and it would see service with all of the Allied forces, Russians, British, and Anzacs in all theaters. Ultimately, over 600,000 would be produced by the end of World War II alone. Adaptable like the universal carrier, the Jeep was put to work in tasks as wide-ranging as a mobile mortar platform, artillery towers, a field ambulance, and just about everything in between. It was the personification of battlefield flexibility and agility. The Humvee is the natural inheritor of the Jeep legacy. A high-mobility, multi-purpose wheeled vehicle, the Humvee began life as a project to find a single vehicle that could be used to perform a multitude of functions in combat.
A Humvee is effectively a Jeep replacement. It's a four-wheeled vehicle, that's the main variant, that is able to transport troops very quickly from one location to the other.
For nearly 30 years, the Humvee has been the workhorse of militaries across the globe. And like its predecessor, it has achieved iconic status as one of the most recognizable vehicles on the planet. It can operate on 40% of side slope, climb a 60% slope, ford 1.5 meters of water, and is fast enough to keep up with the Abrams tank. Despite its size, 1.8 meters high, 2.1 meters wide, and 4.5 meters long, like the Jeep, the Humvee is a relative lightweight, tipping the scales at 2,600 kilograms. But what really sets it apart from the Jeep is its cabin, which offers full occupant protection. And to achieve the low weight necessary for high-speed agility and soldier safety, that cabin is largely constructed of aluminium.
And what we find with aluminium alloys is that for lighter weight vehicles, ballistically, they generally perform better than high-strength steels. But that can come with its own difficulties.
Seeing service in the Middle East during the First Gulf War, the Humvee proved to be the ultimate in agility and adaptability. But war is constantly changing. The widespread introduction of IEDs, or improvised explosive devices, have made the lightly built Humvee vulnerable. And a replacement is on the way. A replacement designed to protect the occupants from not just IEDs, but also weapons like HIMARS. The purpose of HIMARS is to clear a path for infantry, tanks, and traditional artillery by engaging and destroying virtually any enemy asset within its target area. It does this by launching its weapons at a distance, after which it moves away from the area at speed before enemy forces locate the launch site. Featuring a 6-shot Mars rocket launching module attached to the flatbed of a modern multi-purpose heavy truck. At 7 meters long, 2.4 meters wide, and with a height of just 3.2 meters, the HIMARS is remarkably compact, given its destructive capability. In a typical mission, HIMARS would travel at over 85 kilometers per hour to a designated launch location, where a command and control post would transmit selected target data to the onboard launch computer. The computer then aims the launcher and provides prompts to the crew to arm and fire a pre-selected number of rounds, a sequence that takes just 16 seconds. Firing an array of guided missiles with ranges up to 100 miles. Most rockets fired by HIMARS carry a payload of several hundred anti-material grenades, which are dispersed over the target in midair and detonate on impact, destroying or disabling all enemy assets in the designated area. HIMARS is an incredibly agile, modern expression of a weapon that prior to World War II lived solely in our imaginations. The missile. Missiles are the ultimate in agile attack weapons. Ones that leave an enemy with little time to defend or respond. And the faster the missile, the harder it is to destroy. What's more, they can be launched with a flick of a switch, delivering a massive payload without any human risk to the operator. All sides in World War II were looking at rockets of one kind or another. But it was the Germans who took what were, at the time, storybook musings and created a most agile and deadly reality. A reality that would change the face of modern warfare. A long-range pilotless flying bomb that in World War II was accompanied by a sound that would live in the minds of the British for decades. The Treaty of Versailles, signed after World War I, forbade the defeated Germans from developing any new artillery weapons. But it said nothing, however, of rockets. With Hitler's rise and a determination that technology would win the next war, the Germans committed huge resources to the development of rocket-powered weaponry. They called them vengeance weapons. The V-1 was a pilotless jet-powered plane with an explosive warhead. Over 8 meters long and with a wingspan of over 5 meters, it was launched by igniting its pulse engine and firing it on a sled up an inclined ramp 36 meters long. The V-1 was then thrown into the air in much the same way that an aircraft carrier launches planes. Once airborne, it simply continued toward its target in the same direction it was launched, using a preset magnetic gyro compass.
The V-1 Doodlebug is guided by gyroscopes and a flight termination system basically running on a timer. So it will fly a particular time in a particular direction, and then it will dive at the ground and explode.
Initially designed to power into the ground, a fault in the fuel system of the V-1's engine caused it to cut out as it dived.
And of course, there's stories around London of people knowing that they were about to have a V-1 attack when you heard the pulse jet go across the sky and then cut out. And you knew that some short time later it would be impacting somewhere in the city.
And when it did, it was devastating. The Doodlebug, or Buzz Bomb as it became known, carried a 1-ton warhead that was detonated by immediate action fuses on impact, sending its blast outwards across the surface. Over 4 months, more than 9,000 were launched, primarily at London, with devastating effect. But the V-1 had a range of just 321 kilometers. And by late 1944, Allied advances in Europe, along with sustained bombing, had destroyed and pushed back its launch sites, making London safe from the Buzz Bomb. But worse was to come. As the war turned decidedly in the Allies' favor, the Germans took one last technological roll of the dice and introduced a supersonic weapon that could neither be tracked, intercepted, nor chillingly heard.
The V-2 is probably best described as the first ballistic missile. Many of the technical innovations that were necessary to build a useful rocket were solved by Wernher von Braun and the German design team with the V-2.
First launched in September 1944, the V-2 was a potent, destructive weapon designed to breed terror in civilian populations. It succeeded, and it also killed thousands. With over 3,000 fired at England, Belgium, and France in a 6-month reign of terror, before the Allies overran their launch sites in early 1945. a silent killer, it was also a scientific marvel, one that would change the course of humanity.
The V2 was the first man-made object that actually reached the boundary of space, which we normally define to be 100 kilometres above the Earth's surface. And they actually did that during the Second World War, arguably at the point where they're on the point of losing as well. So quite a technical achievement.
The most fundamental hurdle that needed to be solved to build a useful rocket was the development of a method for combining liquid fuel and oxygen under sufficient pressure to generate the required thrust. To do this, they designed turbopumps powered by household chemicals like hydrogen peroxide. Simple bleach that mixed and compressed the fuel before it was driven at pressure into the firing chamber. A principle that is central to rocket propulsion systems to this day. While it terrified the Allied nations, the V2 had a relatively small effect on the war. Its primitive guidance system didn't allow it to strike strategic objectives such as bridges, factories, or airfields. But it was perhaps the most astounding technological development of the war. And like so much German World War II technology, V2 rockets and scientists captured at the end of the war would form the basis of US and Russian missile programs that would, very quickly, change the world forever.
At the end of the war, von Braun was captured by the Americans. He was an SS officer. But pragmatic politics, the Americans decided not to prosecute, to bring him home and use him as an engineering leader.
Given the relative immaturity of ballistic missile technology, neither Russia nor the US achieved usable ballistic missiles immediately after the war. Both had atomic weapons, but in the late 1940s and early 50s, most of the competition between the two countries revolved around gravity bombs delivered by strategic bombers. But the race for supremacy was forever changed by the events of 1952, with the successful full-scale test of a workable hydrogen bomb.
The power of these weapons was very scary for them at the time. Both the Russians and the Americans ended up running experiments and test detonations where the yield was much higher than they expected.
With both countries in possession of H-bomb technology, the race was on to find a way to deliver the warhead. And when in 1957, the Soviets launched a multi-stage ballistic missile, as well as the first man-made satellite, Sputnik, the Americans quickly responded with the SM-65 Atlas, the world's first nuclear-armed intercontinental ballistic missile. More than simply an Americanized vengeance weapon, the Atlas was designed to fly in excess of 10 times the range of a V2, 5,500 kilometers from the United States to strike at the heart of the Soviet Union. On its parabolic journey, it would fly between 150 and 400 kilometers into space, from where the warhead, separated from the main stage rocket, would transition in orbit until it plunged back to Earth and exploded over the desired target. A large task, and given that the heavier the rocket, the more power required to launch, huge efforts were made to trim its bulk. Even so, the Atlas at 25 meters high weighed over 108 tons, and like the V2 and many rockets to this day, much of that weight was its propellant, a mixture of kerosene and liquid oxygen. It proved to be a definitive design.
Intercontinental ballistic missiles and space rockets have almost identical types of characteristics, and so the Atlas still sees service today, basically into the 2000s.
The Atlas was the first stage in a dangerous game of brinkmanship, and was produced in sufficient numbers that, had they been fired, we would be living in a very different world today. But such was the paranoia that surrounded the Cold War. Obvious deterrents were not enough to stop development. The fear amongst Americans was that if they were attacked, the Atlas would be too slow to respond.
So one of the problems with a nuclear war such as they envisaged in the Cold War is that it's incredibly destructive. There is the risk that if somebody starts a war, then it will very quickly get out of hand and you'll end up with a bloodbath on both sides, with most of the belligerent countries' territory destroyed and most of their population dead. The concern was, how do you stop this scenario from happening? How do you stop someone from starting a nuclear war?
The solution was immediate launch capability. Enter the Minuteman. The Minuteman was so named because, like its colonial namesake, it could respond immediately to threat. But to respond to the press of a button required solid fuel.
One of the normal problems with rockets is that they're all liquid-fueled. The problem with that is liquid propellants. You can only hold them in the rocket for a short period of time before you have to remove them and probably refurbish the rocket to make up for the fact that it's been fueled, which means they're not a very good deterrent because you can't keep them in a ready-to-launch state. But the Minuteman brings forward a solid rocket propellant, which means that it can sit in the silo ready to go at a moment's notice, and they don't degrade very much over time, so 15 to 20-year lives are not unusual.
Rapid advances in solid fuels left just the question of accuracy.
The other revolutionary part of the design was the navigation system.
To fly a ballistic trajectory and hit a designated target demands a very accurate inertial navigation system that uses gyroscopes spun up and aligned to the Earth's rotation.
And there's not time to do that. It might take anywhere up to half an hour for that gyroscope to align. So consequently, with the Minuteman, the gyroscope's already spun up, ready to go.
With its underground silos able to withstand a nuclear blast, retaliation was guaranteed. The epitome of agility and the ultimate stalemate weapon. If the Minuteman is ever truly fired, what is certain is that both sides will lose. Man has long applied the latest science to the creation of weapons, but the industrial age has seen unprecedented leaps in man's capacity to manufacture ever more powerful machines. Machines capable of inflicting death and destruction on a massive scale. From hand grenades to howitzers, flamethrowers to high explosives, and of course, the ultimate in devastation, the atom bomb. This is the story of modern man's insatiable desire to land the killer blow on the pathway toward mass destruction. Cannons first appeared on battlefields in the late 1300s. And during the Middle Ages, they became standardized, more common, and more effective, both in siege roles and against infantry. Effectiveness that led Shakespeare in his play Henry IV to have the character Falstaff describe his men before battle as food for powder. Cannon fodder was to become the popular term, but not even Shakespeare could have imagined the power of the artillery designs of the 20th century. Technology that would create food for powder, the like of which had never been seen before. The French 75. The gun from which all modern field artillery is descended. The Canon de 75 Model 1897 was the world's first truly modern artillery piece and instantly made every other field gun in the world obsolete.
Every major offensive that the French army took part in France on the Western Front during the First World War, the French 75 would be the key part in the preliminary artillery bombardment.
Weighing only 1,500 kilograms in action, it fired a 75mm shrapnel round weighing 7 kilograms out to a range of 6,850 meters. But what was revolutionary about the French 75 was that its 7-man crew could maintain a steady firing rate of up to 15 rounds per minute. This unprecedented ability to provide rapid, accurate fire was achieved by using a new and ingenious hydropneumatic recoil system.
The recoil mechanism in the French 75 meant that it would come automatically back to its originally fire position and did not have to be re-aimed before it was fired again.
The entire cycle, including the return, took just 2 seconds. The gun also featured an all-new rapid-acting screw-type breech mechanism, into which was loaded an innovative fixed round, with the time-fused, shrapnel-filled projectile and propellant charge pre-packaged in a brass case, which could be loaded in a single action. A combination of innovations in a single weapon that led to destruction on a scale that had never been seen before. It is estimated that the Allies alone fired over 5 million tons of shells during the Great War, and the Germans perhaps as much again. In all, over 1 billion projectiles plunged through the air in just 4 years. And when it wasn't raining lead, a deadly fog would drift in. On the evening of April 22, 1915, Allied troops looking across no man's land in southern Belgium saw a strange greenish-yellow cloud drifting toward them. The Germans had released 170 metric tons of chlorine gas along a 6-kilometer stretch of the front. More than 1,100 troops would be killed and 7,000 injured in what was the world's first large-scale use of chemical weapons. The confined trench systems of World War I were ideal for achieving effective concentrations of gas. However, when it was released from cylinders on the prevailing wind, as it was that day, it was impossible to control. Firing gas at the enemy using artillery was the solution. Chemical shells were first introduced by the Germans in 1916, using 150mm artillery. Independent of the wind, delivery of chemicals became a much more accurate affair. But gas, like any weapon, evolves as a result of battlefield experiences. The main flaw associated with delivering gas via artillery was the difficulty of achieving a killing concentration. Each shell carried only a small payload, and an area needed to be saturated to produce a cloud to be deadly. And both sides developed countermeasures, some primitive, others, like gas masks, becoming increasingly sophisticated. To nullify this, in 1917, the Germans introduced a chemical which did not need to form a concentrated cloud to be effective. Mustard gas. A volatile, oily liquid that was heavier than air. Having settled on the ground and in the soil, mustard gas remained active for weeks, even months, depending on the weather conditions. Poisoning was by contact. Troops would march through contaminated areas, unaware that they were being exposed. After returning to their trenches or barracks, they would then contaminate other soldiers. After contact, the skin of victims would blister. Troops would begin to vomit, suffer internal bleeding, and eventually blindness. Between 35 million and 66 million shells filled with chemicals were fired during World War I. Although the strategic power of gas was not in the number of soldiers it killed, less than 1% of fatalities and only 7% of casualties were attributed to chemicals. It was in the psychological terror they caused. Fear that in World War II would be delivered by size. And on land, the largest Allied weapon of the Second World War was the American M1. Introduced in 1943, the Black Dragon, as it was called, was designed to penetrate thick concrete fortifications, like those the Allies expected to encounter along the German Siegfried Line. And the key to its destructive power was its caliber.
The larger the caliber, the faster the projectile, the higher the payload you can accelerate. You deliver a much more intense, a much more dangerous explosive payload to the target.
In the case of the Black Dragon, that amounted to a huge 240mm explosive projectile that weighed 160 kilograms, fired out of an 11-meter-long barrel to a distance of 23 kilometers with pinpoint accuracy. Each shell impact from the M1 left a crater more than 2 meters deep and 8 meters wide, and the radius in which a soldier could be rendered a casualty was unprecedented. For an unentrenched prone man up to 40 meters from detonation, death was almost certain. At 100 meters from the blast, that same man would have a 50% chance of becoming a casualty. And potentially deadly shrapnel fragments could be thrown as far as 1 kilometer away from the point of impact. But the Black Dragon was a towed artillery piece. Before it could be fired, it had to stop, uncouple, set up, and dig in. To fully exploit a tactical advantage on an increasingly mobile battlefield, it soon became clear that the artillery most capable of capitalizing on that advantage should also be mobile. All arms battle is dependent on uniform speed of action, tanks, infantry, and artillery all working together. And as the Cold War got chilly, the Americans introduced a mobile weapon of extraordinary destructiveness, the M109. The original M109 was introduced in 1962. And with its 7th update, the Paladin, every aspect of its destructive capability has been enhanced.
The M109 Paladin is a self-propelled howitzer. And so what that means is that you have a 155mm gun fitted to a vehicle chassis.
The addition of gun stabilization systems, automated gun laying and loading systems to the 1960s chassis makes the Paladin capable of sustaining 4 rounds per minute for 4 minutes without fully emplacing. Together, a battery of 6 Paladins can deliver over a ton of ordnance per minute for each of those 4 minutes, an immense weight of destructive power delivered to a target. And the firing range of the Paladin has been extended from 24 to 30 kilometers with conventional shells by fitting of a longer, lighter 6-meter barrel, range that extends to 40 kilometers with the use of rocket-assisted guided projectiles. And it is those shells that do the damage. Improvements in high tensile steel has led to a reduction in the thickness of shell walls without loss of structural integrity, which has in turn allowed shells to carry more explosives. This, combined with improved explosive compounds, give the M109 Paladin a casualty effect 400% greater than a similar weapon from World War II. Less steel, more destructive power, more accurately delivered. The M109 is currently undergoing a further update that will no doubt increase its ability to deliver heavy blows from well behind the front lines. But for an infantryman in the heat of battle, destruction is up close and much more personal. Small bombs have been used in warfare since ancient times. The Greeks deployed firebombs in antiquity, and since the invention of gunpowder, early versions of hand grenades with dangerously unpredictable smoldering fuses had been cautiously deployed, mainly in siege situations. Considered obsolete at the outset of World War I, the demands of trench warfare saw the idea of hand grenades resurrected, redesigned, and emerge as an indispensable item in the foot soldier's arsenal. Grenades put the destructive power of an artillery strike in an infantryman's pocket. And while initially they were thrown, the desire to project them farther led to developments that allowed the infantryman to expand his destructive reach beyond arm's length. In the latter stages of World War I, riflemen, Lewis gunners, and grenadiers were joined by the rifle grenadier. Rifle grenadiers fired a standard grenade fitted to a steel rod launched from an infantry rifle, using a blank charge out to a range of up to 150 meters. A cup-type launcher was introduced later in World War I, a system that persisted through World War II, but using a propellant to kick the projectile out of a barrel creates recoil, and it is recoil that limits both the range and the size of the projectile that can be fired. It was the adoption of the high-low pressure ballistic principle that revolutionized grenade launchers and led to weapons like the M203. The projectile in the M203 is set in a bi-chambered cartridge case with propellant cup fitted into the base. The cup contains the propelling charge and acts as the high-pressure chamber. And the hollow cavity of the case, which surrounds the cup, acts as the low-pressure chamber. When fired, the high pressure does not directly act on the projectile, as it would in a standard gun. But instead, that pressure is allowed to bleed gradually into the hollow outer cavity at a controlled rate. This lower pressure then shoves rather than kicks the projectile out of the barrel at a constantly increasing muzzle velocity, dramatically reducing recoil. As a result, the M203, which weighs just 1.5 kilograms and attaches under the barrel of an infantry rifle, fires a relatively large 40mm shell, weighing 1/4 kilogram, out to a range of 400 meters from a standing position. Weight and range that with a standard firing system would produce recoil beyond human capabilities. And each high explosive grenade carries 32 grams of modern composition B explosive.
And once you detonate the explosive, that sets up a chemically supported shock wave within the explosive material. That shock wave would move between 5 and 8 kilometers per second. And it's the shock wave that does the damage to vehicles, it kills people, and it destroys structures.
While they don't release shrapnel in the quantities of the French 75, M203 shells have a similar casualty radius, and the arsenal includes rounds that can breach 75 millimeters of steel and a range of incendiary grenades. But incendiary weapons, like so much of the machinery of war, have a history all of their own. In August 1942, when the U.S. Marines began the offensive on the Solomons Island of Guadalcanal, they encountered numerous underground fortifications built by the Japanese. Direct assaults on those interconnected tunnels proved extremely costly. And to clear them, the Americans turned to a weapon that had, in the past, proved ideal for aggressive assaults on bunkers and entrenched positions: the flamethrower.
Fire in warfare is as old as warfare itself. You can go all the way back to the use of Greek fire, all that sort of thing. So it's not surprising that developers, inventors, and the military themselves started looking at how to make use of fire or flame.
First introduced onto the battlefields of World War I by the Germans in late 1914, the demoralizing physical and psychological effects of the new weapon that spewed flames 18 meters were immediately felt by the Allies.
You have 2 tanks. One tank will hold your gas, in this case nitrogen gas. The other tank will hold your flammable liquid. The nitrogen gas will drive the petrol down the pipe. So when you pull the trigger, you're releasing an element of the gas which will be pushing the petrol out.
As World War II approached, the basic fundamentals of the World War I design remained unchanged: a flammable liquid propelled by a gas. Although technological advances added to their lethality by introducing lighter cylinders, making flamethrowers man-portable. Of course, portable is a subjective term, and the American M1 flamethrower weighed a sizable 32 kilograms. But they proved indispensable in certain situations.
In the main, they were used for structures to suppress bunkers, examples of which would be the use of flamethrowers on Okinawa and coming ashore at Normandy.
While the M1's range was greater than those of World War I, at just 40 meters, it involved the operator exposing most of his body when engaging suspected enemy positions. And the size of the tanks and general stance of the infantrymen using a flamethrower made for a tempting target.
They're carrying what amounts to a flammable bomb on their back. They're very vulnerable.
Ultimately, portable flamethrowers gave way to tank-mounted flame guns, which offered better range, protection for the crew, and made for a far more imposing threat. A threat that would, of course, be countered. Little more than a century ago, at the Battle of Cambrai, the world witnessed the first mass attack by an innovative British weapon, inspired by simple farm machinery. Despite early examples being slow, cumbersome, and unreliable, they very quickly developed, and in less than 20 years, they had transformed the battlefield.
If it's a straight tank versus infantry unit battle, pity the poor infantrymen. However, if you can come up with a weapon that's flexible enough to get it into position when you need it, to put overwhelming force on one spot on that tank, well, that's the goal of the anti-tank role.
By World War II, improvements in the internal combustion engine gave tanks greater speed, heavier armor, and more lethal weaponry. The need arose for a mobile weapon that could put the power to stop them in the hands of an infantryman.
This war moves fast. The Germans and Italians found that out in Africa. We picked up some things, too.
The bazooka.
The famous American bazooka, nicknamed after the musical instrument that it resembled, is a simple tube, the mechanical firing mechanism, sort of like a giant gun, but it's essentially a guidance tube, or an initial guidance tube, for this projectile.
The recoil was balanced by the countering forces of the projectile exiting the front of the tube and the propellant exiting at the rear. With the pistol grip and shoulder support made of wood, the unit weighed just 6.5 kilograms. And it was easy to operate between a crew of two, one to load and the other to fire the 60mm projectile, which was capable of piercing armor up to 102 millimeters thick. Against all German tank types, often a single well-placed shot was all that was needed. However, success was not guaranteed.
You have the ability to reload. Very important when you're trying to engage tanks. You might miss the tank. You might simply damage the tank. So to be able to fire more than one shot, a reusable system is very useful.
It was such an effective, portable, destructive force that close to 500,000 bazookas, along with over 15 million rockets, were produced. But the Americans were not alone in looking to put highly destructive capabilities into the hands of their infantry. The Cold War-era RPG-7 can trace its roots back to the bazooka, and like its forebear, this Soviet system follows the same simple principle of a reloadable tube that fires a rocket-propelled projectile. The differences between the two are in the missile.
It looks like it's got a stick with a double conical shape on the end of the stick. When it's launched, there are fins that deploy, there's spring-loaded fins that open up, and that provides drag stabilization to the weapon system as it flies through the air.
The RPG-7's rocket is initially thrown clear of the tube by a booster charge. Once in motion, the acceleration sets off a pressure-generated spark that ignites a sustainer motor, which accelerates the projectile once it's 11 meters from the launcher. By using this two-stage firing mechanism, the RPG-7 cuts the tube length from 1.5 meters, as it was on the bazooka, to just 90 centimeters. Projectiles up to 93 millimeters in diameter and 4.5 kilograms in weight are fired at a velocity of 294 meters per second. And the warhead makes up most of the weight, which, combined with the extra kinetic energy imparted by the rocket's vastly superior speed, means the RPG-7 can penetrate standard armor as thick as 750 millimeters. But by far, the RPG-7's greatest asset is its simplicity of construction, which has seen over 9 million enter service since 1961.
It's prolific, it's widespread, and the technology is reasonably old, but it's simple. Lots of Soviet engineering was simple and effective, and the RPG-7 is no exception.
The RPG-7 uses what is called a shaped charge, which is lethal against traditional armor. Suddenly, tanks were beatable, but in modern warfare, no single machine completely dominates for long. All weapons develop in response to improvements in others. The improvements in armor-piercing rounds saw the design tension between armor and anti-tank weaponry swing in favor of the weapon. With tanks rendered increasingly vulnerable, designers hit back in the 1970s with even more sophisticated defense systems.
So one of the ways in which protection can be offered against something like a shaped charge weapon system, such as an RPG-7, is by using explosive reactive armor.
Explosive reactive armor consists of sheets or slabs of high explosive sandwiched between two plates. When hit by a shaped charge, the explosive detonates, driving the plates apart and damaging the incoming projectile. Not so with the munitions fired by the Javelin, which use an ingenious tandem warhead.
The Javelin is a guided missile, and it carries on it a shaped charge weapon system, so when it makes contact with the vehicle, it detonates the explosive that propels a high-velocity copper jet into the armor of the vehicle.
A smaller precursor charge prepares the way for that copper jet by pushing through the explosive reactive armor and clearing a path for the larger main warhead to penetrate the target's primary defenses. Using a command launch unit that incorporates an integrated day-night sight, the missile is thrown free at launch, and like the RPG-7, only fires its rocket motor once clear of the crew. Engagement of airborne, static, or mobile ground-based targets is accomplished using either the traditional direct fire line of sight method or with help from the missile's inbuilt infrared guidance system, which can be programmed to attack armored vehicles at their weakest point. It does this by climbing to 150 meters as it reaches the target, and then rapidly descending from a steep angle with devastating effect.
Tank armour on its roof is inherently thin across the board, so now you've got projectiles that are actually smashing down through the top of tank turrets rather than trying to penetrate through.
The Javelin is the latest in highly mobile battlefield destruction. But destruction on a far bigger scale gets delivered not from on the battlefield, but rather from above it. For the first time in man's history, World War I introduced the concept of what we now refer to as total war. And with the entire resources and populations of the belligerent nations mobilized towards the war effort, with every human resource considered a functioning part of the enemy's war machine, city factories, warehouses, and even civilian populations, not just the military, became legitimate targets. And during World War II, the rapid development of aircraft, in particular the long-range heavy bomber, elevated the concept of total war to a new level. delivering wholesale destruction on entire cities, the like of which had never been seen before. On the 14th of March, 1945, the first of 42 new bombs were deployed over Germany's industrialized Ruhr Valley. Officially, they were uninspiringly designated as the bomb medium capacity. Unofficially, they were called Grand Slams. 8 meters long and shaped like an artillery shell, the Grand Slam's warhead, which contained 4,000 kilograms of Torpex, an explosive 50% more powerful than TNT, was detonated after the bomb had penetrated deep into the earth, giving a localized earthquake effect equivalent to 3.7 on the Richter scale. And the aircraft that carried these massive munitions was the Avro Lancaster.
When it was designed, it was supposed to carry about 4,000 pounds of bombs. The British discovered that in fact it was such a strong and robust airframe that it could carry more. So they invented the Grand Slam, 22,000 pounds. That's 5 times the bomb carrying capacity than when the aircraft was designed.
The Lancaster was born of the early wartime experience of the Avro Manchester, a twin-engine bomber first flown in 1939. Within mere months, it became clear that the all-new Manchester simply couldn't carry enough bombs far enough. Avro took the Manchester, revised the wing, added 4 12-cylinder Rolls-Royce Merlin engines, and in early 1942, within just 18 months of being conceived, the Lancaster entered service.
It was one of those examples of an aircraft which is designed and which is perfect from the beginning. So most of the Lancasters that were built and flown were Lancaster B1s. No, there wasn't a need for many subsequent marks. It didn't continuously improve.
Using an all-metal construction that maximized structural strength per weight, the Lancaster was agile, easy to fly, and capable of withstanding serious levels of damage in flight. And the durability of the design was enhanced by the fact that both the fuselage and the wings were assembled in modules, 5 apiece.
But it was quite novel at the time. But it was built in sections, and that meant that it could be repaired in sections. So if you came back from Dusseldorf with a hole in your wing, the wing was replaced. It's an example of where the RAF, indeed the aircraft manufacturers, are adapting their construction methods to meet the needs of the people who fly this machine, because they always came back damaged.
In all, Lancasters flew 156,000 operations, and alone dropped over 618,000 tons of bombs over Germany between 1942 and 1945, destroying entire cities.
And it did persuade the Germans that the war wasn't happening in Russia or in North Africa or in Normandy, it was happening in your street. So the bomber offensive, I think, was a crucial arm of the British war effort, especially the British war effort. And the Lancaster is at the heart of that.
The Lancaster was one of the most iconic machines of World War II, a big, slow-moving bomber that operated in huge formations. The Lancaster was not intended to evade enemy defenses so much as beat them into submission. But the years after the Second World War saw a shift in thinking when it came to strategic bombing. In early 1946, the U.S. Air Force issued a brief for a strategic bomber that flew above defenses with the range to carry out missions independent of bases controlled by other countries. And so in 1948, Boeing put their faith in a new engine and pushed the design envelope as far as they thought possible. What emerged from that process was an aircraft with a wingspan of 56 meters that would incorporate the 2 great aeronautical advances of the time: the enduring B-52 Stratofortress.
The B-52 bomber used a swept wing design and was purely jet engine powered, with a long, narrow fuselage which was primarily a series of bomb bays combined with 8 engines on the wings.
These advances gave the B-52 an operational range in excess of 14,000 kilometers, a top speed of 1,047 kilometers per hour, and a service ceiling of 16,000 meters, which allowed it to launch a strike from well outside enemy territory. And its extended range provides it with the capacity to loiter outside a combat zone while enemy defenses are subdued and targets are identified. Most of the lower central fuselage of the 48-meter-long aircraft is given up to the storage of a 31,500 kilogram payload, with the B-52 capable of carrying a most astounding array of munitions in its bulky frame.
It was designed at the very beginning of the Cold War and subsequently has outseen designs that were supposed to replace it. So many people thought that it would no longer be in operation, but it still is.
The B-52 is a great example of the speed of aircraft development in the years following World War II. It boasted 5 times the payload of the Lancaster, an aircraft that less than 10 years previous had been the supreme Allied strategic bomber. And it delivered that destructive force 3 times as quickly and 4 times as far. It is another example of an aircraft, like the Lancaster, that they just managed to get right the first time. But aircraft development during the Cold War didn't stop with the B-52. The combination of cabin pressurization and jet engine technology provided bombers like the B-52 with their main defensive capability: altitude. At 15,000 meters, they were able to operate safely, well beyond the range of conventional ground-based anti-aircraft weapons. But by the early 1960s, new radar-guided surface-to-air missiles had changed the rules yet again. High-altitude bombers suddenly became vulnerable. To defeat these systems, General Dynamics responded with what was an all-new concept: a long-range supersonic bomber that, rather than flying even higher, would evade radar detection by skimming close to the ground. The F-111 Aardvark.
The main system that we had to help fly at low altitude was the train-following radar. So this was a forward-looking radar that actually gave us an interpretation of the terrain in front, and we could link it in with the autopilot system on the aircraft such that it would actually fly. You could fly hands-off at anywhere from 200 feet to 1,000 feet, any speeds up to 600 knots plus if you really wanted to go that fast.
That terrain-following radar system, which is standard in most of today's fighter jets, was untried when the F-111 was first flown in 1964 and gave the aircraft unprecedented assault capabilities. Undeterred by weather or darkness, the F-111 could enter enemy territory below radar level and proceed to attack its target at incredible speed. And it was equipped with 2 of the most powerful turbofan engines ever fitted to a production aircraft, that also boasted another technological first: afterburners.
Basically, the afterburner system is you just pour a whole bunch of fuel down the back of the engine and light it up. And that's pretty much it. And it just gives you extra thrust.
Commonplace now, afterburners gave the F-111 extraordinary performance capabilities. By using those afterburners, it could climb at close to 8,000 meters per minute and reach its service ceiling of 20,000 meters in less than 3 minutes. That puts the F-111 in strike fighter class even today. But despite being designated F for fighter, the F-111 was a genuine fighter bomber designed to carry a 13,500 kilogram payload. To create an aircraft that could perform well under load at low speed, take off and land from short runways, and yet still fly at over Mach 2, required another groundbreaking innovation: variable geometry, or what we know as swing wings.
If you look at a slow-speed aircraft, you'll see that it has a fairly straight, sort of fat wing. A lot easier to generate lift at slower speeds that way. As you want to go faster, you actually want to go to more of a delta shape, which is predominantly the sort of shape that you see in high-speed aircraft. And that's where you start sweeping the wings back to 72 degrees.
The F-111 remained in service with the US and Australian Air Forces for 30 years. But like the B-52, the F-111 was principally designed during the Cold War to deliver a weapon of such destructive power that when it was unleashed in 1945, it changed the planet forever. In 1939, a letter delivered by the esteemed physicist Albert Einstein to the then US President Franklin D. Roosevelt resulted in the United States taking a gamble. As World War II erupted into a destructive global conflict, Roosevelt ordered the establishment of the US Uranium Project to investigate the possibility of creating a controlled chain reaction. In June 1942, the Uranium Project fell under the control of the US military and was renamed the Manhattan Project. And in December of that year, under a Chicago football stadium, the world's first controlled nuclear reaction was achieved. With the war looking more and more like it would end in an Allied defeat, what followed was the birth of the single biggest weapons development project the world had ever seen.
The Manhattan Project that the Americans developed, which was the scientific and the military development of these weapons, was just enormous. I mean, literally hundreds of thousands of workers worked on sites, 17 sites in 12 states. Huge secret cities built across the US, all feeding into this enterprise.
It was a colossal program. One team at Los Alamos, led by Robert Oppenheimer, worked on the physics of the bomb. Huge industrial plants in Tennessee and Washington state were established to extract the plutonium, each arm of the massive operation working in extreme secrecy. After 5 years of frenetic research and billions of dollars, on July the 16th, 1945, the Manhattan Project came to fruition. A device was successfully exploded in the New Mexico desert. With a force of 22 kilotons, the equivalent of 22,000 tons of TNT, it dwarfed anything that had come before it.
One of the most profound and moving aspects of the whole atomic weapon story is that the men, mostly men, the men who developed the bomb, were the first to become aware of what the destructive capacity of the bomb was. And they debated within themselves whether or not they should be allowing this to happen. And I think one of the considerations that swayed them into regarding this as being justifiable was that many of them knew exactly what they were up against. Many of them were Jewish refugees from Nazi Germany who knew what had happened to Europe's Jews and knew the costs of not defeating Nazi Germany.
And while the atomic bomb may have been designed with Germany in mind, by the time the atomic bomb was completed, Hitler was gone and the Germans had surrendered. But the Allies were still at war with Japan. A little after 8:15 a.m. on the 6th of August 1945, the Enola Gay, a heavily modified B-29 bomber, dropped a device measuring just 3 meters in length, 71 centimeters in diameter, and weighing just 4,000 kilograms over the unsuspecting Japanese city of Hiroshima. Hiroshima, a manufacturing center of 350,000 people, located about 800 kilometers from Tokyo, had not been randomly selected as a target for the atomic bomb. It had been chosen. Firstly, because up until this point in the war, unlike Tokyo, it had been largely unscathed by conventional bombing. And secondly, because the city was flat.
the bomb went off. 3.5 kilometers of destruction, a fireball that big, killed probably 80,000 people more or less instantly, wounded about another 80,000 people. And because it was a flat site, the impact of the bomb went for miles and in a circular way, diminishing as it progressed, but still devastating, utterly destroying this city.
When Little Boy, as the bomb was called, detonated 580 meters above the city, it did so with a force equivalent to 15,000 tons of TNT. As it exploded, intense heat rays and radiation were released in all directions. And almost instantly, 13 square kilometers of that city was transformed into ruins. And when that city's devastation failed to elicit a Japanese surrender, just 3 days later, a second weapon, Fat Man, was deployed. But heavy smoke and cloud cover over the city of Kokura caused a mid-mission diversion to the secondary target, the port city of Nagasaki.
Not an ideal target from the bomb maker's point of view because it was a hilly, it was in a valley, and so the blast was constrained. But even so, it killed 40,000 people.
Fat Man had an energy yield of approximately 22 kilotons of TNT, and the fireball caused by the explosion was 280 meters in diameter, creating a surface temperature of around 5,000 degrees Celsius. The role of the two weapons in ending the war remains the subject of ongoing debate. Emperor Hirohito's decision to surrender was also influenced by Russia's invasion of Manchuria and declaration of war against Japan on August 8th. But one thing is certain: the world has never been the same since.
One of the claims that's made about the use of Little Boy and Fat Man on Japan was that one of the major reasons for doing it was not so much to defeat Japan, but to signal to Russia that the US had this incredible new capability. Whether that's true or not, I certainly don't know. But what is certainly true is that the creation of atomic weapons radically changed the global strategic environment.
A change that would lead to a 40-year period of uncertainty known as the Cold War. In 1945, there had been just 3 nuclear weapons on the planet. By 1950, there were 304, 299 in the US arsenal, and 5 in the Soviet Unions.
So we entered into the era of the Cold War, and it was a Cold War for a reason. Although there were many hotspots, the two great powers that were competing never went to war against each other. And probably the main reason for that is the existence of nuclear weapons.
But even a Cold War can be won. Determined to maintain their lead in what was now a nuclear arms race, in October 1952, the Americans conducted Operation Ivy on the Eniwetok Atoll in the Marshall Islands. The plan was to detonate a device named Mike, an experiment with a higher-yielding form of nuclear explosion that derives a significant proportion of its explosive energy from fusion. A thermonuclear device, Mike was the first of what we now know as a hydrogen bomb. At 7:15 a.m. local time, on the 31st of October 1952, Mike was detonated from a control ship stationed 55 kilometers away. The detonation resulted in a massive explosion equivalent to 500 times the explosive force of the bomb dropped on Nagasaki just 7 years earlier.
4, 3, 2, 1.
After the test was confirmed to the public, Time magazine reported that the force and horror of atomic weapons has entered a new dimension. The first full-dress H-blast turned the mid-Pacific sandspit named Illusiolab into a submarine crater. And indeed, it had. Illusiolab, the atoll on which Mike's detonation took place, was vaporized. The explosion produced a fireball 6 kilometers in diameter and a mushroom cloud 160 kilometers wide. Unsurprisingly, In 1952, it was the largest nuclear explosion ever detonated. And as the tests continued on both sides, and with the development of missiles to deliver warheads, the numbers of nuclear weapons skyrocketed, a proliferation that changed the nature of warfare.
At the heart of the idea of nuclear deterrence is something called mutually assured destruction, or MAD. And that term is quite literally chosen. The idea is that you would be simply mad to start a nuclear war, because where the other side had the ability to wipe you out if you launched against them, and they had the ability to launch before you could guarantee that you'd taken out all of their nuclear capabilities, in starting a war, you would essentially choose to destroy yourself.
In 1955, there were 2,636 warheads, of which the Americans had 2,400. By 1965, that number had increased to over 35,000, as the US and Russia battled for supremacy. With enough weapons to destroy the planet several times over, an uneasy status quo emerged.
Great powers simply couldn't afford to go to war with one another. And that's what nuclear deterrence relies on. The incredible power of the opposing nuclear forces means that there are no rational ways to start a war with one another.
At the height of the third phase of the Cold War, the world was home to over 61,000 nuclear weapons. That number has now dropped to a little over 16,000. But should they ever be used, mass destruction would result of a kind that the men of World War I, a mere 100 years ago, could never have imagined.